Hello there, and welcome to Science for Sleep, where curiosity slows down a little, the universe feels softer around the edges, and even the oldest light in existence has enough patience to wait quietly for us to notice it. Tonight, we're travelling farther than almost any human journey has ever gone. Not with rockets, or warp drives, or dramatic countdowns shouted through loudspeakers, but with something much stranger and much calmer. We're going to travel with light itself, ancient light. Light that began moving across the universe so long ago that Earth did not yet exist. The oceans did not exist. The sun did not exist. Not even the Milky Way looked anything like the galaxy we know today. Somewhere unimaginably far away sits a galaxy with the wonderfully complicated name JADES-GS-Z 14-0, a name that sounds less like a cosmic wonder and more like a password you forget 5 seconds after creating it. And yet this tiny smudge of light may be the oldest galaxy humanity has ever seen, or at least the oldest one we've found so far. The truly astonishing part is not just its age, it's the fact that its light survived the entire history of the universe just to arrive here now, landing delicately inside a telescope orbiting 1.5 million kilometers from Earth. After 13.5 billion years of travel, after crossing expanding space, dodging clouds of gas, and surviving the violent evolution of the cosmos itself, those photons finally reached us. Which means that somewhere in the universe, a very ancient galaxy has been patiently sending us a message since before our planet was born. And tonight, we're going to sit quietly with that idea for a while. Before we begin though, I'd love to know something. Where in the world are you listening from tonight? Is it late evening where you are? Early morning? Are you tucked into bed already, sitting near a window, travelling somewhere, or perhaps listening with one eye still open, while insisting to yourself that you're definitely not sleepy yet? And what time is it in your little corner of Earth right now? Funny, really. We're about to spend hours talking about distances so enormous that human history disappears into insignificance, and yet our lives still revolve around tiny glowing numbers on clocks. Midnight, 2 a.m, 11:47 p.m. The universe deals in billions of years, while we still get mildly stressed because the microwave says there's only 8 seconds left. If you find this journey relaxing or interesting or simply a pleasant way to drift towards sleep, I'd be very grateful if you liked the video and subscribed. It helps this calm little corner of science reach more people who might need a quiet evening among the stars. Now then, let's settle in. You don't need to understand astrophysics tonight. You don't need equations or advanced mathematics or the ability to pronounce every galaxy name correctly on the first attempt. Frankly, astronomers barely manage that themselves sometimes. All you really need is curiosity. Because this story begins with something humans have always struggled to understand properly. Darkness. Real darkness. Not the kind you get during a power outage, where your phone screen still lights up your face like a tiny artificial moon. Not the darkness of a countryside road or a cloudy night. Those places still exist inside a mature universe, already crowded with stars and galaxies. The darkness we're talking about tonight came before almost everything. To understand why JADES-GS-Z 14-0 matters so much, we first have to imagine the universe before galaxies properly existed. A time before spiral arms, before planets, before constellations, before anything familiar decorated the sky. And strangely enough, the story begins not with stars, but with silence. The early universe was not silent in the ordinary sense, of course. It was unimaginably energetic, violent beyond description, temperatures so extreme that matter itself struggled to exist in stable forms. But there were no observers, no ears, no worlds, no oceans to carry sound, only expansion. Only energy cooling and spreading through newborn space. When people hear the phrase Big Bang, they often imagine an explosion happening somewhere in empty darkness, like fireworks going off in space. But that picture is misleading. The Big Bang was not an explosion inside the universe. It was the rapid expansion of space itself, everywhere expanding at once. No center, no edge, no cosmic fireball sitting in the middle while debris flew outward. And for a while, the universe was too hot for atoms to even exist properly. That detail matters more than it sounds. Imagine trying to build something delicate while standing inside a blast furnace. Electrons could not settle down around nuclei because the temperatures were simply too intense. Matter existed as a dense plasma, glowing brilliantly but also trapping light completely. In those earlier stages, the universe was opaque. Light existed, certainly, huge amounts of it, but photons could barely travel any distance before crashing into charged particles. The cosmos was like an endless fog made of pure energy. Then gradually, over hundreds of thousands of years, things cooled enough for atoms to finally form. This moment is called recombination, which sounds oddly like a corporate merger between very enthusiastic chemistry departments, but it marks one of the great turning points in cosmic history. Once electrons settled into stable atoms, light suddenly gained freedom. The fog lifted. Photons began travelling across the universe uninterrupted. Some of that ancient radiation still exists today. We call it the cosmic microwave background, the oldest light we can directly observe, a faint afterglow from the infant universe itself. And after that light spread outward, something curious happened. Darkness returned. Not complete darkness, perhaps, but something close enough that modern astronomers gave it an appropriately dramatic name, the Cosmic Dark Ages. This period lasted for millions upon millions of years. No stars yet, no galaxies, only vast clouds of hydrogen drifting through expanding space. It's difficult for modern humans to picture because our skies are crowded with structure. Even on a cloudy night above a city, there are satellites, airplanes, distant streetlights reflecting off the atmosphere. Complete emptiness feels unnatural to us. But the young universe spent an astonishingly long time waiting for gravity to begin assembling the first great structures. Gravity, meanwhile, was already hard at work. Tiny fluctuations in matter density left over from the early universe began growing slowly over time. Regions with slightly more matter pulled in additional matter. Bit by bit, clouds formed. Then larger clouds, then denser regions. Gravity is patient like that. It does not rush. Give it enough time and even thin gas drifting through space can become stars, galaxies, clusters, and eventually planets, covered in creatures who stay awake at midnight wondering about ancient galaxies with impossible names. The first stars likely appeared around 100 to 200 million years after the Big Bang. That sounds ancient to us, but cosmologically speaking, it happened remarkably quickly. And these first stars were probably very different from the stars we see today. Modern stars contain heavier elements like carbon, oxygen, silicon and iron, because earlier generations of stars created those materials through nuclear fusion. But the first stars had almost none of that. The universe initially contained mostly hydrogen and helium with trace amounts of lithium. That means the earlier stars may have grown enormous. Some models suggest they reached hundreds of times the mass of our Sun. Huge, hot, short-lived, and incredibly bright. These stars burned through their fuel rapidly and exploded violently, enriching the universe with heavier elements for the first time. Without those early stars dying, planets like Earth could never form. Your bones contain calcium forged inside ancient stars. The iron in your blood was created through stellar processes billions of years ago. Which means this story about ancient galaxies is also quietly a story about you. Not metaphorically. Literally. Every atom in your body has cosmic ancestry. And somewhere during this era of first stars and violent formation, the earliest galaxies began emerging from the darkness. Small at first, chaotic, nothing like the elegant spirals we associate with galaxies today. Modern galaxies look organized because they've had billions of years to evolve. Early galaxies were messy places, gas clouds colliding, stars forming rapidly, radiation blasting through turbulent regions, matter still assembling itself into recognizable structures. The young universe was not calm, it was busy becoming itself. For decades, astronomers tried to push farther back into this ancient era using increasingly powerful telescopes. Every new instrument revealed older galaxies, older stars, more distant objects, but eventually they reached a frustrating limit. The universe itself was hiding its earliest history from us, partly because distant galaxies are extremely faint. Their light stretches as the universe expands, shifting toward longer wavelengths in a process called redshift. This happens because space itself expands while light travels through it. Imagine drawing waves on a balloon, then inflating the balloon. The waves stretch farther apart. Light behaves similarly across expanding cosmic distances. By the time ancient light reaches Earth, wavelengths originally emitted as visible or ultraviolet light may arrive as infrared radiation. And Earth's atmosphere is rather annoying about infrared observations, useful for breathing, less helpful for ancient cosmology. So astronomers needed something new, something colder, something far from Earth, something capable of detecting extremely faint infrared light from the edge of cosmic history. For years, people talked about the successor to the Hubble Space Telescope, almost like it was a scientific myth. An impossibly ambitious machine requiring technologies never before attempted at such scale. The project faced delays, budget problems, engineering nightmares. At one point, it reportedly required over 300 single-point failure risks to work correctly during deployment, meaning hundreds of things that absolutely could not fail, which is not the sort of statistic that helps engineers sleep peacefully. The telescope eventually became known as the James Webb Space Telescope. And unlike Hubble, Webb was designed specifically to see deeper into infrared wavelengths, deeper into the ancient universe, deeper into time itself. Because looking far away in space is also looking backward in time. That idea deserves a moment to settle in properly. Nothing we see exists exactly as it is now. Moonlight is already over a second old when it reaches Earth. Sunlight takes about 8 minutes to arrive. The nearest star beyond the Sun appears to us as it existed more than 4 years ago. And distant galaxies, millions, billions, sometimes over 13 billion years in the past. Astronomy is fundamentally an act of historical observation. Telescopes are time machines, not metaphorically, but physically. Every improvement in telescope technology extends humanity's view farther backward across cosmic history, and Webb was built for exactly that purpose. When it finally launched in December 2021, there was enormous tension surrounding the mission. Webb's folded mirror and tennis court-sized sunshield had to deploy perfectly in space. No astronauts could repair it easily. Unlike Hubble, Webb orbits far beyond the Moon near a gravitational balance point called L2. If something failed, that would likely be the end. So engineers watched anxiously as the telescope unfolded piece by piece across space. Mirror segments aligned, sunshield deployed, systems cooled, instruments activated. And then Webb began looking outward. What happened next surprised even many astronomers. The early universe appeared brighter, more active, and more crowded with galaxies than expected. Not gradually evolving into complexity over enormous timescales, but seemingly assembling large structures very quickly. And among the astonishing discoveries emerging from Webb observations was one faint ancient galaxy buried deep inside a survey called JADES. JADES stands for the JWST Advanced Deep Extragalactic Survey. A name far less catchy than oldest galaxy in the universe, admittedly, but astronomers do love their acronyms. Inside this survey, researchers identified an object with an astonishing redshift value around 14, meaning we are seeing it as it existed only about 290 million years after the Big Bang. That is incredibly early. The universe at that point was barely beginning its long history. Earth today is about 4.5 billion years old. This galaxy's light began travelling toward us almost 9 billion years before our planet existed. Dinosaurs were still absurdly far in the future. Continents did not exist. Nothing human even remotely imaginable existed. And yet the light survived, across expanding space, across cosmic evolution, across the formation of galaxies, stars, planets, oceans, civilizations, languages, telescopes, and sleepy YouTube videos, until finally one species on one small world looked upward and noticed it. There is something deeply calming about that. The universe does not hurry. Galaxies are born. Stars die. Light travels for billions of years without complaint. Meanwhile, humans become impatient waiting for elevators. Perspective can be wonderfully relaxing sometimes. Still, the discovery of JADES-GS-Z14-0 did more than simply break records. It raised difficult questions. Because according to many earlier models, galaxies this bright and developed should not have existed so soon after the Big Bang. The young universe may have formed structure faster than scientists predicted, and whenever the universe behaves differently than expected, astronomy becomes especially interesting. Scientists love being correct, of course, but discoveries become truly exciting when nature quietly says, "Actually, it's a little stranger than you thought." That strange possibility is part of what makes Webb's discoveries feel so important. We're not merely filling in details. We're entering territory where our understanding itself may need adjustment, and perhaps that is fitting. After all, every generation thinks it understands the cosmos fairly well right before the universe casually reveals something enormous hiding in the darkness. In the centuries ahead, humans may discover galaxies even older than JADES-GS-Z14-0. Webb itself may uncover more ancient structures still waiting quietly at the edge of visibility. Perhaps someday another telescope will look farther back yet, toward the first stars themselves, toward the moment the cosmic darkness first began breaking apart. Try to imagine a universe without stars for a moment. Not a cloudy night sky where the stars are hidden behind weather. Not a city sky washed pale by streetlights and glowing windows. A universe genuinely without stars. No galaxies hanging in the distance. No planets. No constellations. No familiar points of light at all. Only darkness gradually unfolding across expanding space. It feels strange because our brains are used to structure. Humans naturally organize the sky into patterns. We connect stars into hunters and bears and mythological creatures carrying swords for reasons nobody fully questions anymore. We name galaxies. We label nebulae. We divide the cosmos into understandable pieces because our species is deeply uncomfortable with enormous unnamed emptiness. But there was a time before any of that existed. Long before galaxies had names. Before galaxies had shapes. Before galaxies properly had identities at all. The universe was still trying to become a place where such things were even possible. And oddly enough, the story starts with conditions so extreme that almost every normal human comparison completely fails. The early universe was not hot in the way fire is hot. It was not bright in the way sunlight is bright. Those words become almost meaningless at sufficiently cosmic scales. Temperatures shortly after the Big Bang reached levels where matter behaved in ways that feel completely disconnected from everyday experience. At the earliest moments we can meaningfully discuss, the universe was filled with an incredibly dense soup of fundamental particles and radiation. No atoms, no chemistry, no recognizable matter, just energy and expansion. And importantly, the universe was tiny compared to today. Not tiny in the sense of floating inside something larger. There was no outside container waiting around the edges. Space itself was compressed into a vastly smaller state. This is one of those ideas that tends to make the human brain quietly sigh. and request a cup of tea. Because instinctively we imagine expansion happening into something. A balloon expands into a room, smoke expands into air, ripples spread across water, but the universe does not expand into external space. Space itself expands, which sounds suspiciously like the sort of sentence philosophers invent to avoid paying taxes, but in cosmology, it's genuinely the best description we have. Distances between regions of space increase over time because the fabric of space changes. And during the earliest moments after the Big Bang, those changes happened astonishingly fast. There was a period called cosmic inflation, during which the universe expanded exponentially in an incredibly tiny fraction of a second. In an instant almost beyond comprehension, microscopic quantum fluctuations became stretched across enormous scales. Those fluctuations would later matter tremendously. Tiny irregularities in density eventually became the seeds of galaxies. That means the enormous cosmic structures we see today may owe their existence to minute quantum variations in the earliest universe. Little imperfections amplified over billions of years by gravity. In a way, every galaxy exists because the universe was not perfectly smooth. Perfection, cosmically speaking, would actually have been rather disappointing. A perfectly uniform universe might never have formed stars or planets or people. Matter would remain evenly distributed forever. No structure, no clustering, no galaxies drifting across the darkness, just endless sameness. Instead, tiny variations gave gravity something to work with, and gravity is wonderfully persistent. It's also surprisingly weak compared to the other fundamental forces. A small refrigerator magnet can defeat the gravitational pull of the entire Earth on a paperclip, which feels mildly insulting to gravity when you think about it. Yet gravity possesses one tremendous advantage. It accumulates. Over enormous timescales, even weak attraction becomes transformative. And time, as the universe quickly demonstrated, was something it had plenty of. In the first seconds after the Big Bang, the universe expanded and cooled rapidly enough for the simplest particles to stabilize. Quarks combined into protons and neutrons. Matter began settling into more recognizable forms. Within minutes, nuclear fusion briefly transformed parts of the young cosmos into a gigantic primordial furnace. This era, called Big Bang nucleosynthesis, produced most of the universe's hydrogen and helium, and then fusion largely stopped. The universe expanded too quickly for heavier elements to form efficiently during this stage. That detail becomes extremely important later because early cosmic chemistry was remarkably simple. Hydrogen dominated everything. Helium came second. Almost nothing else existed yet. No oxygen, no carbon, no iron. No calcium for bones, or silicon for rocks, or gold for jewellery people insist is subtle, despite reflecting sunlight directly into your eyes from across entire restaurants. The universe initially lacked nearly all the elements required for planets and life. Those would need to be manufactured later inside stars, which means stars are not just decorative cosmic objects, they are chemical factories, engines transforming simple matter into complexity. But before stars could exist, the universe had another problem to solve: light itself. For hundreds of thousands of years after the Big Bang, space remained filled with hot ionized plasma. Electrons moved freely instead of binding to atomic nuclei. Photons constantly scattered off charged particles. Light could not travel cleanly through the universe. Imagine trying to see through dense fog illuminated by headlights from every direction at once. Photons continuously bounced around without getting far. The young universe was opaque, and this lasted much longer than most people expect. Human minds often compress cosmic history into dramatic cinematic moments. Big Bang, stars appear, galaxies form, done. Real cosmology is slower, far slower. The universe spent roughly 380,000 years waiting for conditions to cool enough for electrons and nuclei to combine into neutral atoms. When that finally happened, everything changed. Suddenly photons could travel freely. The cosmic fog cleared. Radiation streamed across space largely uninterrupted. That ancient light still surrounds us today as the cosmic microwave background, discovered accidentally in 1965 by two radio astronomers named Arno Penzias and Robert Wilson, which is one of science's more charming stories. They were working with a giant antenna and kept detecting mysterious background noise they could not eliminate. At one point they even considered whether pigeons living inside the equipment might be responsible. Imagine discovering evidence from the early universe while initially suspecting bird-related interference. Science is glamorous sometimes. Eventually researchers realized the signal came from every direction in space. A faint microwave glow left over from the early universe itself. Not ordinary starlight, not radiation from galaxies, something vastly older, a fossil from cosmic infancy. When scientists map this background radiation, they are effectively looking at the oldest directly observable light in existence. And remarkably, the universe at that time appears extraordinarily uniform, with only tiny fluctuations in temperature and density. Tiny, but not zero. Again, those imperfections mattered. Without them, gravity would have nothing to amplify. Now, once neutral atoms formed and radiation moved freely, the universe entered a long, strange period often called the Cosmic Dark Ages. This phrase sounds dramatic enough to belong in a fantasy novel involving cursed kingdoms and suspiciously attractive wizards, but astronomers use it very literally. The universe became dark because stars had not formed yet. No major sources of visible light existed. There was still radiation from the cosmic microwave background, of course, but as expansion continued, that radiation stretched into longer wavelengths and gradually cooled. So for millions of years, the cosmos drifted through relative darkness. Hydrogen clouds floated through expanding space, while gravity slowly strengthened tiny density differences. Nothing happened quickly. That's important to remember because modern humans live surrounded by rapid processes. Messages travel instantly. Videos load in seconds unless your internet provider has entered one of its mysterious emotional phases again. Entire news cycles rise and collapse before breakfast. Cosmic evolution operates differently. Gravity takes its time. A cloud of gas does not become a galaxy overnight. Matter slowly gathers into denser regions over enormous timescales, and during the cosmic dark ages the universe was quietly preparing for its first great transformation, the birth of stars. Now, the first stars were probably unlike most stars alive today. Modern stars form in environments already enriched by earlier stellar generations, but the first stars emerged in a chemically primitive universe, containing almost only hydrogen and helium. That changes everything. Heavier elements help cool gas clouds during star formation. Without those elements, clouds in the early universe may have formed much larger stars than we typically see today. Some theoretical models suggest the first stars reached hundreds of solar masses, gigantic, blindingly luminous, and tragically short-lived. Large stars burn fuel rapidly. They live fast and die violently. These early stars likely exploded as massive supernovae, blasting newly forged heavier elements into surrounding space for the first time. Carbon, oxygen, iron, the ingredients of future planets and life itself. So the earlier stars were not merely points of light ending cosmic darkness. They were chemical pioneers transforming the universe into a place capable of greater complexity. And they probably formed in clusters inside early dark matter halos. Dark matter, meanwhile, deserves at least a gentle introduction because it quietly dominates the structure of the universe while remaining frustratingly invisible. Astronomers discovered something peculiar while studying galaxies and galaxy clusters. Visible matter alone could not explain observed gravitational effects. Galaxies rotated too quickly. Clusters held together more strongly than expected. Something unseen contributed additional mass. That unseen component became known as dark matter. Not because it's evil or particularly moody, but because it does not interact significantly with light. As far as we know, dark matter neither emits nor absorbs electromagnetic radiation in ordinary ways, yet gravity reveals its presence. Today, dark matter appears to make up most of the matter in the universe. And in the early cosmos, dark matter played a crucial role by creating gravitational scaffolding around which ordinary matter accumulated. Think of it like invisible valleys forming in space. Hydrogen gas gradually fell into these gravitational wells, eventually becoming dense enough to ignite the first stars. Without dark matter, galaxies may never have formed properly at all, which means much of cosmic history depends heavily on something we still do not fully understand. The universe is wonderfully rude like that sometimes. Just when humanity begins feeling clever, reality quietly reminds us that most matter remains mysterious. Now, once the first stars ignited, the universe entered another transformative era known as cosmic reionization, a complicated name for a dramatic process. Radiation from early stars and galaxies began ionizing surrounding hydrogen gas. The neutral universe gradually became transparent again across large regions. Little bubbles of ionized gas expanded outward around galaxies. Over time, these bubbles overlapped and spread until much of intergalactic space became ionized. This process fundamentally changed the appearance and behavior of the cosmos. And somewhere during this turbulent age, the earliest galaxies emerged. Not elegant spirals like the Milky Way, not calm, mature systems drifting peacefully through space. Early galaxies were chaotic construction zones. Gas collapsed rapidly. Stars formed aggressively. Radiation flooded outward. Collisions occurred frequently because the young universe was denser and smaller than today. Galaxies merged constantly. Structure assembled itself through turbulence and gravity working together across enormous scales. Astronomers sometimes describe galaxy formation as hierarchical. Small structures form first, then merge into larger systems over time. But Webb observations have complicated that picture somewhat, because galaxies like JADES-GS-Z14-0 appear surprisingly evolved, surprisingly early. And that's part of what startled astronomers so much. According to many earlier models, there should not have been enough time for galaxies to grow this massive or luminous only a few 100 million years after the Big Bang. Yet, there it was. Ancient light arriving from a galaxy already shining brightly near the dawn of cosmic history. To appreciate how extraordinary that is, it helps to understand just how young the universe truly was during that era. Imagine compressing the entire 13.8 billion-year history of the universe into a single calendar year. The Big Bang occurs at midnight on January 1st. The Milky Way forms around March. The Sun and Earth appear in early September. Dinosaurs emerge around Christmas Day. Human civilization occupies only the final seconds before midnight on December 31st. In that analogy, JADES-GS-Z14-0 appears astonishingly early in January, practically at the beginning, and yet somehow it already existed as a recognizable galaxy. That's why researchers became so interested in it. The discovery potentially hints that stars formed faster, galaxies assembled earlier, or the young universe behaved differently than expected. Perhaps all three. Astronomy advances through precisely these moments. Someone builds a better telescope. The universe reveals something unexpected. Scientists revise theories. Then new observations create new mysteries. It's less like assembling a completed puzzle, and more like discovering the puzzle occasionally changes shape while you're working on it. The James Webb Space Telescope was specifically designed to peer into this ancient era. Its infrared capabilities allow it to detect light stretched dramatically by cosmic expansion. Remember, ancient ultraviolet and visible light arriving from distant galaxies becomes shifted into infrared wavelengths during its journey across expanding space. Hubble could glimpse parts of the early universe, but Webb pushes farther back, closer to the beginning. And what Webb found surprised many researchers almost immediately. The early cosmos appeared crowded, bright galaxies emerged faster than expected, massive structures formed quickly. It was as though the young universe became productive unusually early, almost impatient. Though cosmically speaking, impatient still means processes unfolding across millions of years, which remains slightly slower than most modern software updates. Still, one of the calming things about cosmology is how thoroughly it dismantles the illusion that everything must happen quickly. The universe does not rush to become beautiful. Stars take time, galaxies take time, planets take time. Even light itself travels patiently across billions of years without concern for schedules. And perhaps that's partly why these ancient galaxies feel emotionally powerful to us. They remind us that existence operates comfortably at scales far beyond ordinary human urgency. Right now, photons from distant galaxies continue crossing intergalactic space silently. Some may eventually reach future civilizations billions of years from now. Some may travel forever without ever striking anything at all. Light simply continues, patiently. Meanwhile, here on Earth, one small species recently learned how to build instruments sensitive enough to catch ancient photons arriving from the edge of observable history. And those instruments are beginning to reveal that the first galaxies may have appeared earlier than we imagined. That realization changes how we think about cosmic evolution itself, because before galaxies had names, before spiral arms and stable structures emerged, before the universe looked remotely familiar, something astonishing was already happening in the darkness. Matter was organizing itself. Gravity was constructing the first luminous systems. And somewhere among those ancient structures, one galaxy eventually produced light that would survive almost the entire lifetime of the universe, before finally arriving at our telescopes. There is something deeply unsettling about a sky with no stars. Humans rarely experience true darkness anymore. Even in remote places, aircraft blink overhead, satellites drift silently across the night, and distant cities stain the horizon with artificial glow. The modern world hums constantly with light: street lamps, screens, dashboard displays, tiny glowing chargers beside beds that somehow illuminate entire rooms despite being the size of a grape. We live surrounded by brightness, which makes it difficult to imagine that the universe itself once spent millions of years in near-total darkness. Not metaphorical darkness, actual cosmic darkness. A time before stars had formed. A time before galaxies shone across space. A time when the universe drifted through vast cold expanses filled mostly with hydrogen gas and invisible gravity, quietly preparing the future. This period, known as the Cosmic Dark Ages, remains one of the strangest eras in cosmic history because it was both empty and enormously important. Nothing dramatic appeared to happen for a very long time, and yet almost everything that would eventually matter depended on what occurred during this silent age. To understand the Cosmic Dark Ages properly, it helps to remember what happened just beforehand. Roughly 380,000 years after the Big Bang, the universe cooled enough for electrons and atomic nuclei to combine into neutral atoms. Radiation finally escaped freely across space, producing the cosmic microwave background. The fog lifted. The universe became transparent, but transparency is not the same thing as illumination. Once that ancient radiation stretched and weakened through cosmic expansion, space entered an age with very few visible light sources. There were no stars yet, no galaxies, no blazing quasars, only darkness spreading across expanding space, and it lasted an astonishingly long time. Modern humans are uncomfortable with long waiting periods. If a microwave takes 90 seconds, many people stare through the glass like abandoned Victorian widows waiting for ships lost at sea. The universe, meanwhile, spent tens of millions of years calmly preparing for its first stars. Patience on cosmic scales feels almost absurd compared to human timescales. Still, the darkness was not entirely empty. Hydrogen and helium drifted through space in enormous clouds. Tiny fluctuations in matter density, inherited from the earliest moments after the Big Bang, slowly grew under the influence of gravity. Those fluctuations were incredibly small. Differences in density measured mere fractions of a percent. But gravity does not require dramatic beginnings. It only requires time. Given enough time, even slight imbalances grow larger. Regions with marginally more matter pull in additional matter. Denser areas strengthen gravitational attraction further. Gradually, structure begins emerging from near uniformity. It's a bit like watching droplets form on a fogged window very slowly. At first, the surface appears evenly covered. Then tiny irregularities strengthen over time until larger patterns emerge. Except in the universe, the process unfolds across millions of years and distances so enormous that ordinary language begins struggling to keep up. During the Dark Ages, the cosmos looked nothing like the structured universe we recognize today. No spiral galaxies rotated through space, no planetary systems orbited stars, no heavy elements existed in significant quantities. Chemically speaking, the universe remained extremely simple. Hydrogen dominated everything. Helium came second. That was largely it. No oxygen for water, no carbon chemistry, no iron cores, no rocky planets, no biology. The ingredients for future complexity did not yet exist. And perhaps that's one of the strangest things about the cosmic Dark Ages. The universe already contained the potential for everything we know, but almost none of the actual structures themselves. Like a blank sheet of music before the orchestra begins. Or perhaps more accurately, like ingredients sitting untouched in an unimaginably large cosmic kitchen, while gravity quietly considered recipes. Now, during this era, dark matter continued shaping the evolution of structure behind the scenes. Dark matter remains one of the greatest mysteries in modern science, because nobody knows exactly what it is. Astronomers infer its existence through gravitational effects, but it neither emits nor reflects light in ordinary ways. And yet dark matter dominates the universe gravitationally. In fact, ordinary matter, the stuff making up stars, planets, teacups, and suspicious leftovers in refrigerators, represents only a small fraction of total cosmic matter. Most matter appears invisible, which feels slightly unfair considering humanity spent centuries inventing telescopes specifically to look at things. Still, dark matter provided the scaffolding necessary for galaxies to eventually form. Invisible dark matter halos emerged first. Ordinary gas then fell into these gravitational wells. Over time, hydrogen clouds became denser and hotter, and eventually, somewhere in the darkness, the first stars ignited. But before we reach that moment, it's worth lingering inside the Dark Ages a little longer, because this period reveals something profound about the universe. Namely, the cosmos does not begin fully assembled. That may sound obvious, yet humans instinctively expect finished structures. We see the Milky Way and unconsciously assume galaxies simply belong in reality. We treat stars as normal features of existence. But there was a time when stars did not exist. The universe had to build them. And building anything across cosmic scales takes extraordinary amounts of time. Imagine floating through intergalactic space during the Dark Ages. Not that surviving would be particularly likely. You would freeze, suffocate, and become an unfortunate example in several astrophysics lectures almost immediately. But hypothetically speaking, what would you see? Very little. The cosmic microwave background still filled space, though already stretched into microwave wavelengths invisible to human eyes. Hydrogen gas drifted through darkness. Tiny density variations slowly evolved under gravity. No constellations, no sunrise, no bright galactic disks decorating the sky. The universe would feel eerily unfinished and silent. Not silent in the everyday sense, because sound cannot travel through vacuum effectively anyway, but silent in the emotional sense, a cosmos still waiting for its first lights to switch on. There is something oddly calming about that idea. Modern humans often imagine progress as rapid and continuous, but the universe itself spent enormous stretches of time in states that appeared almost uneventful. Complexity emerged slowly. The stars were not rushed into existence. Now eventually gravity pushed certain hydrogen clouds toward collapse. As gas accumulated inside dark matter halos, temperatures rose, pressure increased, density climbed, and then, for the first time in cosmic history, nuclear fusion ignited inside stellar cores. The first stars were born. Astronomers often call these hypothetical earlier stars population 3 stars, which sounds slightly like a backup droid army from a science fiction film, but the naming system simply refers to stellar generations. Population 1 stars are younger, metal-rich stars like our Sun. Population 2 stars are older stars with fewer heavy elements. Population 3 stars represent the first generation, formed before heavier elements existed. Curiously, nobody has directly observed a true population 3 star yet. They may have all died billions of years ago, but based on models of the early universe, scientists believe these first stars were probably enormous, very enormous. Without heavier elements to cool collapsing gas clouds efficiently, the earliest stars likely accumulated tremendous masses before stabilizing. Some may have exceeded 100 times the mass of the Sun, possibly even more. These stars would have burned incredibly hot and bright. And because massive stars consume fuel rapidly, they probably lived short, violent lives. A star much larger than the Sun can exhaust its fuel in only a few million years. By cosmic standards, that is astonishingly brief. Then came the explosions, supernovae. The deaths of the first stars transformed the universe permanently. Inside stellar cores and supernova blasts, fusion created heavier elements for the first time: carbon, oxygen, silicon, iron. The chemistry of the universe changed forever. Without those early stars dying, planets could never form properly later on. Neither could life. Your body exists because ancient stars exploded. Not metaphorically, literally. The calcium in your bones, the oxygen you breathe, the iron carried through your blood, all originated in stellar furnaces somewhere across cosmic history. That realization never really stops being astonishing. Every human is assembled from recycled cosmic material, and during the cosmic dark ages none of that yet existed. The universe had not built the chemistry necessary for future complexity. In a sense, the dark ages were the long, quiet preparation before cosmic creativity truly began. Now, once the first stars ignited, their radiation began changing, surrounding space dramatically. Ultraviolet light from these stars ionized nearby hydrogen gas, ripping electrons away from atoms again. Little expanding bubbles of ionized gas formed around early stars and primitive galaxies. Gradually these bubbles overlapped. Over millions of years, much of the universe transitioned from neutral hydrogen back into ionized plasma. This process is known as reionization, and it marks one of the great turning points in cosmic history because it transformed intergalactic space itself. The first stars did not merely illuminate darkness, they altered the state of the universe, and somewhere within this chaotic era, the earliest galaxies emerged, not graceful spirals yet, more like turbulent gatherings of gas, stars, radiation, and dark matter. The young universe was messy. Modern images of galaxies often look calm because mature galaxies can settle into stable structures over billions of years. But the early cosmos resembled a cosmic construction site. Gas clouds collided constantly. Stars formed aggressively. Radiation flooded space. Everything evolved quickly. Ironically, after millions of years of relative darkness and slow preparation, the universe suddenly became astonishingly energetic once stars appeared. And this is part of what makes discoveries like JADES-GS-Z14-0 so fascinating. That galaxy existed shockingly early, which means all these processes — gravitational collapse, star formation, chemical enrichment, galaxy assembly — may have happened faster than many earlier models predicted. The universe seems to have become complicated remarkably quickly, and that raises wonderful questions. How rapidly can structure emerge from simplicity? How soon after the Big Bang could galaxies truly form? Did the first stars appear earlier than expected? Did dark matter behave differently? Or are our models of early galaxy formation still incomplete? Astronomy progresses through questions like these. Every telescope extends the frontier slightly farther backward in time, and every new frontier reveals additional mysteries waiting in the dark. The James Webb Space Telescope was designed specifically to study these ancient epochs because the first stars and galaxies remain extraordinarily difficult to observe directly. Remember, the universe expands while light travels. That expansion stretches wavelengths through redshift. Light originally emitted in ultraviolet or visible wavelengths from the first galaxies arrives today shifted deep into infrared. By the time ancient photons reach Earth, after over 13 billion years of travel, the universe has stretched them enormously, which means observing the cosmic dark ages and the earliest galaxies requires extremely sensitive infrared instruments, and Webb excels at precisely that task. Before Webb launched, astronomers already suspected the first stars and galaxies formed earlier than previously imagined. Hubble had hinted at surprisingly ancient galaxies, but Webb pushed much deeper. Suddenly, researchers could detect galaxies existing only a few 100 million years after the Big Bang, and some appeared unexpectedly bright and developed, like JADES-GS-Z14-0. That discovery matters because galaxies should theoretically require time to grow. Stars must form, gas must accumulate, structures must merge. Yet this galaxy already existed only about 290 million years after the Big Bang. Cosmically speaking, that is astonishingly early. If the entire history of the universe were compressed into a human lifetime of 80 years, JADES-GS-Z14-0 would appear during the first year and a half. Practically infancy, and yet already a recognizable galaxy. Which suggests the transition from darkness to structure happened incredibly fast. The first lights of the cosmos may have ignited sooner and more efficiently than expected, and perhaps that should not surprise us entirely. The universe often behaves more creatively than human theories initially predict. One generation of astronomers confidently maps reality. Then a better telescope arrives and politely ruins everything. Hubble did this repeatedly. Webb now continues the tradition. Somewhere out there, future observatories are probably preparing to embarrass current theories even further. Science advances beautifully that way, not through certainty, but through increasingly refined surprise. Still, despite all the equations and telescopes and technical terminology, there remains something emotionally powerful about the cosmic dark ages themselves. The idea that the universe once waited in silence before the first stars appeared, before galaxies illuminated the darkness, before anything resembling our familiar sky existed, and then slowly, patiently, gravity assembled the first great lights. One by one, stars ignited, galaxies emerged, the darkness retreated. Eventually planets formed around later generations of stars. Chemistry became richer, complexity increased. Life appeared on at least one small world, orbiting an ordinary yellow star near the edge of an ordinary galaxy. And billions of years later, creatures made from ancient stellar material built telescopes capable of detecting light from those earliest epochs. There is a strange continuity in that. The universe spent millions of years waiting for its first stars, then billions more waiting for observers, and now here we are, lying awake in dark rooms listening to stories about ancient galaxies while photons from the dawn of time continue crossing space above us. Even now, ancient light is still arriving. Some photons entering Webb's mirrors tonight may have begun travelling before Earth existed, before the Sun existed, before the Milky Way finished assembling itself. The darkness of the early universe is not entirely gone. We still carry pieces of it with us. Intergalactic space remains mostly empty. Vast regions between galaxies stretch across unimaginable distances with very little inside them at all. And beyond the observable universe, there may be endless regions humanity will never see because light simply has not had enough time to arrive. Cosmic darkness still surrounds us. But inside that darkness, gravity continues working patiently just as it always has. Stars continue forming, galaxies continue evolving, and somewhere in the distant universe, ancient structures still shine faintly through expanding space, carrying messages from the earliest moments after the first lights finally switched on. For most of human history, the night sky looked permanent. The stars appeared fixed in place, calm and eternal, scattered across darkness in patterns people memorized long before written language existed. Ancient civilizations built myths around them, navigated oceans beneath them, planted crops according to them, and occasionally blamed them for things that were almost certainly not the stars' fault at all. But eventually humans realized something extraordinary. The sky was not merely decoration, it was history. Every point of light represented information travelling across space. The farther away something existed, the older the light became by the time it reached Earth. Looking outward meant looking backward, and once humanity understood that idea properly, astronomy changed forever. Telescopes stopped being simple tools for observing objects and became machines for investigating time itself. Still, seeing the earliest light in the universe turned out to be much harder than anyone expected, partly because ancient light arrives incredibly faint, partly because the universe itself stretches that light while it travels, and partly because Earth, helpful though it may be for breathing and sandwiches and not freezing to death immediately, is actually a rather inconvenient place from which to observe the cosmos. The atmosphere gets in the way constantly. Air moves, heat radiates. Water vapour absorbs infrared wavelengths. The sky glows faintly even at night. It's a little like trying to study fireflies through the steam above a bowl of soup while someone occasionally shakes the table, which is why astronomers gradually began moving telescopes into space. The most famous of these was, of course, the Hubble Space Telescope. When Hubble launched in 1990, it transformed astronomy completely. Suddenly scientists could observe the universe without atmospheric distortion blurring the view. Galaxies appeared sharper. Nebulae revealed astonishing detail. Distant objects emerged from darkness with unprecedented clarity. Though admittedly the telescope's first images were famously blurry because of a mirror flaw, which must have been a deeply stressful week for everyone involved. Fortunately, astronauts repaired Hubble later, and the telescope went on to become one of the most successful scientific instruments ever built. Hubble helped determine the age of the universe more accurately. It revealed black holes lurking at galactic centres. It observed galaxies billions of light years away. And perhaps most importantly for our story tonight, it conducted observations called the Hubble Deep Fields. Astronomers pointed the telescope toward apparently empty regions of sky for extraordinarily long exposures. At first glance, these regions looked dark and unremarkable. No obvious stars, no nearby galaxies, just emptiness. But after Hubble stared patiently into the darkness for days, something astonishing appeared. Thousands of galaxies emerged. Tiny smudges of ancient light filled the image. What seemed empty was actually crowded with distant galaxies extending deep into cosmic history. The deep fields changed the emotional scale of astronomy. People realized that even small dark patches of sky contain unimaginable numbers of galaxies. entire cosmic cities hidden in what looked like nothing at all. And naturally, astronomers immediately wanted to go farther. Older galaxies, earlier epochs, close to the beginning. But Hubble faced a limitation. It primarily observed visible and ultraviolet light, and that becomes a problem when studying the earliest galaxies because of cosmic redshift. Now, redshift is one of those concepts that initially sounds technical and intimidating until you realize it's surprisingly intuitive. Imagine an ambulance driving past with its siren blaring. As it approaches, sound waves compress slightly, making the pitch higher. As it moves away, the waves stretch out, lowering the pitch. Light behaves similarly. When objects move away through expanding space, wavelengths stretch. Visible light gradually shifts toward redder wavelengths and eventually into infrared. And because the universe itself expands while light travels, the oldest light becomes stretched enormously over billions of years. This means the earliest galaxies no longer appear primarily in visible light. Their radiation arrives as infrared. By the time photons from galaxies like JADES-GS-Z14-0 reach us, the universe has stretched them dramatically during their journey. So if humanity truly wanted to see the earliest galaxies, astronomers needed a telescope optimized for infrared astronomy, a much more powerful infrared telescope. That idea eventually became the James Webb Space Telescope. Now, calling Webb the successor to Hubble is technically correct, but emotionally it's a bit like calling a Saturn V rocket a slightly ambitious firework. Webb represented one of the most complex scientific instruments humanity had ever attempted to build, and it took decades. The project began conceptually in the 1990s. Then came years of design work, engineering revisions, delays, technical challenges, budget increases, testing problems, deployment concerns, and enough stress to power entire cardiology departments. At one point, people genuinely worried Webb might never launch at all, because the telescope required engineering solutions unlike anything previously attempted in space. To see ancient infrared light properly, Webb needed to remain extremely cold, very extremely cold. Infrared detectors are sensitive to heat. Even the telescope itself emits infrared radiation if warm enough. So Webb needed protection from sunlight, earthlight and moonlight simultaneously. This led engineers to design one of the most remarkable features of the telescope, the sun shield. Webb's sun shield is enormous, roughly the size of a tennis court when fully deployed. It consists of 5 thin layers designed to block and radiate away heat efficiently. One side of the telescope faces the sun and remains relatively warm. The other side, where the scientific instruments operate, cools to temperatures low enough to observe faint infrared signals from the distant universe. The temperature difference across the shield is astonishing, and the entire structure had to fold up inside a rocket before deploying perfectly in space. Which sounds simple until you remember that space famously offers very few opportunities for second attempts. Unlike Hubble, Webb was not placed in low Earth orbit where astronauts could potentially repair it. Instead, it was sent roughly 1.5 million kilometers away to a location called the second Lagrange point, or L2. Lagrange points are regions where gravitational forces and orbital motion balance in useful ways. At L2, Webb can orbit the Sun alongside Earth while maintaining a stable orientation. This location helps keep the telescope cold and allows continuous observation with the sun shield permanently facing the Sun. It's an elegant solution, terrifying to deploy. Webb launched on December 25, 2021 aboard an Ariane 5 rocket, and then the real anxiety began, because the telescope launched folded. Over the following days and weeks, hundreds of components needed to deploy correctly in sequence: the sun shield, the mirrors, the support structures, everything. Many engineers reportedly described the process as one of the most stressful periods of their careers, which feels understandable considering the telescope cost nearly $10 billion and represented decades of scientific effort. At one point, Webb reportedly had over 300 single-point failure risks, meaning hundreds of components absolutely had to work, no pressure. And somehow, astonishingly, the deployment succeeded, The sunshield unfolded, the mirrors deployed, the instruments cooled, Webb survived. Then came another extraordinary process: mirror alignment. Webb's primary mirror consists of 18 hexagonal segments coated in gold to optimize infrared reflection. These segments had to function together as a single precisely shaped mirror. The level of accuracy required is difficult to comprehend. Tiny adjustments measured in nanometers mattered. Nanometers. Human hair suddenly begins feeling comically oversized in comparison. Eventually the mirrors aligned successfully and Webb began returning test images. Astronomers immediately realized something remarkable. The telescope worked even better than expected, which is the sort of sentence scientists dream about hearing. Webb's infrared sensitivity proved extraordinary. The telescope could detect incredibly faint distant objects with astonishing detail, and soon it began peering deeper into cosmic history than any previous observatory. Now, one of the reasons Webb performs so well is its size. The primary mirror spans about 6.5 meters across, significantly larger than Hubble's mirror. Larger mirrors collect more light, and when studying ancient galaxies, collecting light matters enormously because distant objects are incredibly faint. Remember, photons arriving from galaxies like JADES-GS-Z14-0 have travelled over 13 billion years through expanding space. By the time they reach Webb, only tiny amounts of light remain available for detection. The telescope must gather ancient photons patiently over long exposures. In some ways, observing the early universe resembles listening for whispers during a hurricane while wearing oven mitts and standing very far away. It requires extraordinary sensitivity. And Webb was built precisely for this task. Its instruments can analyze infrared wavelengths across different ranges, allowing astronomers to study the chemical composition, temperature, motion, and distances of ancient galaxies. One particularly important technique involves spectroscopy. Now, spectroscopy sounds complicated, but the core idea is beautifully simple. Light contains information. If you spread light into a spectrum, different elements leave distinct fingerprints through absorption and emission lines. By studying these patterns, astronomers determine what distant objects contain: hydrogen, oxygen, carbon. Various elements reveal themselves through light signatures, and crucially, spectroscopy also allows astronomers to measure redshift very accurately. The farther a galaxy exists from us, the more its spectral features shift toward longer wavelengths due to cosmic expansion. This becomes essential when confirming extremely distant galaxies. Before Webb, astronomers often identified candidate early galaxies through imaging alone, but determining exact distances remained difficult. Webb changed that dramatically. Suddenly researchers could detect and confirm galaxies from astonishingly early cosmic epochs, including JADES-GS-Z14-0. The galaxy emerged from a project called the JWST Advanced Deep Extragalactic Survey, or JADES, which continues astronomy's proud tradition of inventing acronyms that sound vaguely like futuristic software updates. The JADES survey focused on deep observations of distant galaxies using Webb's powerful infrared capabilities, and within those observations, researchers identified something extraordinary: a galaxy with a redshift around 14. That number may not sound dramatic initially, but in cosmology it represents an astonishing distance backward in time. We see JADES-GS-Z14-0 as it existed only about 290 million years after the Big Bang, roughly 13.5 billion years ago. And that means Webb successfully observed light emitted during one of the earliest periods of galaxy formation ever detected. Think about what that really means. Those photons began their journey before Earth existed, before the Sun formed, before the Milky Way fully assembled. They travelled across expanding space through almost the entire history of the universe, and eventually they reached a gold-coated telescope drifting near L2. There is something deeply human about that achievement. For thousands of years, humans looked at the sky wondering what existed beyond visibility. Then gradually we invented lenses, mirrors, detectors, mathematics, rocketry, cryogenic engineering, orbital mechanics, and eventually a machine capable of capturing ancient infrared photons from near the dawn of time. Civilization, for all its chaos and traffic jams and mysteriously disappearing socks, occasionally accomplishes breathtaking things. Still, Webb's discoveries also created complications for cosmology. Because the early universe appeared unexpectedly active, galaxies emerged brighter and more developed than many models predicted. Some researchers expected the earliest galaxies to be tiny, faint systems requiring longer periods to grow. Instead, Webb found surprisingly luminous objects very early in cosmic history, including JADES-GS-Z 14-0, and that forced astronomers to reconsider assumptions about early star formation and galaxy assembly. Perhaps the first stars formed more efficiently than expected. Perhaps gas collapsed faster. Perhaps dark matter halos evolved differently. Or perhaps the universe simply became structurally complex sooner than many theories predicted. Astronomy now stands in one of those fascinating transitional periods where observations advance faster than complete theoretical understanding. And honestly, science becomes especially exciting during moments like that. The universe begins revealing things nobody fully anticipated. Researchers scramble to revise models. Conferences become dramatically more caffeinated. Entire fields suddenly fill with new questions. Webb did not merely improve astronomy incrementally, it opened a new observational era. For the first time, humanity can study galaxies forming near the cosmic dawn with astonishing detail. And perhaps even more astonishing discoveries still wait ahead. Because JADES-GS-Z 14-0 may not remain the oldest known galaxy forever. Webb continues observing. More ancient galaxies may emerge. Future telescopes may push even farther. One day, humanity may observe the first generation of stars directly, or perhaps discover entirely unexpected structures hiding in the early universe. The cosmos rarely runs out of surprises, but tonight, perhaps the most calming thing about Webb is not its complexity or engineering brilliance. It's the simple fact that the telescope exists because humans wanted to know what came before planets, before galaxies matured, before cosmic structure fully emerged. People spent decades building a machine capable of catching ancient light from the edge of observable history. Astronomers are generally careful people. This probably sounds obvious, but it matters more than you might think. When someone claims to have discovered the oldest galaxy ever observed, scientists do not immediately leap from chairs shouting triumphantly while orchestral music swells in the background. Real astronomy is much quieter than that. There are meetings, cross-checks, data analysis, more meetings. Someone inevitably says the phrase, "We should be cautious here," at least 14 times, and for good reason. The universe has a habit of tricking observers, especially when researchers are pushing instruments to their absolute limits. Distant galaxies are faint. Ancient light becomes stretched into infrared wavelengths. Dust can obscure observations. Detector noise can imitate signals. Closer galaxies can masquerade as more distant ones under certain conditions. So when the first hints of JADES-GS-Z 14-0 emerge from Webb observations, astronomers did not instantly announce they had found one of the earliest galaxies in cosmic history. First they checked everything. Then they checked it again. Because the number attached to this object looked almost absurd. Redshift 14. Now, redshift values sound technical and slightly unfriendly at first, but the idea behind them is surprisingly elegant. As the universe expands, light travelling through space stretches along with it. Wavelengths become longer. Blue light shifts toward redder wavelengths. Red light stretches further into infrared. The greater the redshift, the farther light has travelled, and crucially, the farther back in time we are observing. A galaxy with a redshift around 1 appears from a relatively mature cosmic era. Higher redshift reveal progressively earlier periods in the universe's history. By the time astronomers began finding galaxies above redshift 10, they were already probing extremely ancient epochs, but redshift 14, that pushed astonishingly close to the beginning. The light from JADES-GS-Z14-0 began travelling toward us only about 290 million years after the Big Bang. To put that into perspective, the universe today is approximately 13.8 billion years old. This galaxy appeared during cosmic infancy, not adolescence, not early adulthood, infancy. And yet somehow it already existed as a substantial luminous object. That was the shocking part. Because according to many earlier models, galaxies should not have grown so large or bright so quickly. The universe was not expected to organise itself that efficiently so early. And yet there it was, ancient light quietly arriving from an era that should have been far less developed. Now, before Webb launched, astronomers had already identified candidate galaxies from very early cosmic epochs, using the Hubble Space Telescope and other observatories. But identifying extremely distant galaxies is difficult. A faint red object in an image does not automatically mean it exists near the dawn of time. Dusty nearer galaxies can sometimes imitate similar signatures. Astronomers needed something more reliable. That something was spectroscopy, and this is where Webb became revolutionary. Webb does not merely take beautiful pictures, it can spread light into spectra with extraordinary sensitivity, allowing astronomers to identify specific wavelengths and determine precise redshifts. It's a bit like hearing a faint song from another room, and suddenly being able to isolate every instrument individually. Light carries detailed information about its source. When researchers examined the spectrum of JADES-GS-Z14-0, they found something remarkable. The galaxy's spectral features matched an extraordinary redshift value around 14, which meant the light had travelled over 13.5 billion years to reach us. Suddenly astronomers were staring at a galaxy from one of the earliest known periods of cosmic history, and it was brighter than expected. That detail matters enormously. Brightness tells astronomers important things about galaxies. A bright galaxy generally contains significant star formation, or substantial mass, or both. But forming large numbers of stars takes time. Gathering gas into galaxies takes time. Building structure in the early universe takes time. Or at least scientists thought it did. JADES-GS-Z14-0 complicated that assumption. Because somehow, only a few 100 million years after the Big Bang, this galaxy already existed and emitted enough light for Webb to detect across nearly the entire age of the universe. That raised uncomfortable questions. Had astronomers underestimated how rapidly the first stars formed? Were galaxies assembling faster than predicted? Did dark matter halos collapse more efficiently? Were earlier theoretical models incomplete? Or was the young universe simply far stranger than expected? The answer remains uncertain, and astronomers absolutely love situations where the answer remains uncertain, because uncertainty means discovery. Though admittedly it also means many sleepless nights staring at equations while coffee quietly loses hope nearby. Now, the actual process of identifying JADES-GS-Z14-0 involved deep observations from the JWST Advanced Deep Extragalactic Survey, abbreviated as JADES. Astronomers selected regions of sky already studied extensively by previous observatories, and then used Webb's infrared instruments to peer much deeper into the ancient universe. The telescope stared patiently into darkness for long exposures. And this is one of the beautiful things about astronomy. Progress often comes through patience. The universe does not reveal ancient galaxies quickly. Researchers collect tiny amounts of light over many hours. Ancient photons arrive slowly. Detectors accumulate signals gradually until faint objects emerge from cosmic darkness. A distant galaxy does not announce itself dramatically. It appears quietly, almost shyly. One of the most remarkable aspects of the discovery is how small the galaxy initially looked in images. To ordinary viewers, JADES-GS-Z14-0 does not resemble the majestic spiral galaxies commonly seen in astronomy posters. It appears tiny, faint, a little reddish smudge buried among countless other faint objects. And yet inside that tiny patch of light exists an entire galaxy from near the beginning of cosmic history. Billions of stars may already have formed there. The scale becomes difficult for the human brain to process comfortably. Astronomy often creates that effect. Objects appearing tiny in images turn out to contain structures larger than entire galactic systems. Small points of light conceal incomprehensible distances and timescales, and perhaps that's partly why discoveries like JADES-GS-Z14-0 feel emotionally powerful even to people without technical astrophysics backgrounds. Because this is not merely data, it's ancient reality finally becoming visible. The galaxy existed long before Earth formed, long before the Sun existed, long before our galaxy looked the way it does now, and still its light survived. That survival alone feels extraordinary. Imagine beginning a journey before the Milky Way matured and arriving only now. Those photons travelled continuously, while almost everything familiar to humanity came into existence. Dinosaurs rose and vanished during that interval. Continents shifted, civilizations appeared, languages evolved, entire species emerged and disappeared. Meanwhile, the light simply continued moving through expanding space, patiently, quietly, until it reached Webb. Now, another reason astronomers became excited about JADES-GS-Z14-0 involves what the galaxy may reveal about reionization. The early universe initially contained large amounts of neutral hydrogen gas after recombination. This neutral gas absorbed ultraviolet radiation strongly, making certain observations difficult. Eventually, radiation from the first stars and galaxies ionized much of intergalactic space during the epoch of reionization. Understanding exactly when and how reionization occurred remains one of the major questions in cosmology. Galaxies like JADES-GS-Z 14-0 provide valuable clues because they existed during this transformative period. If surprisingly bright galaxies already existed very early, they may have contributed significantly to reionization itself. In other words, ancient galaxies may have helped reshape the entire state of the universe around them, tiny points of light influencing cosmic evolution on enormous scales. And that idea becomes even stranger when you realize how quickly these processes unfolded. Remember, 290 million years sounds immense from a human perspective, but cosmologically, it's astonishingly early. If the universe's history were compressed into a single day, JADES-GS-Z14-0 appears only around half an hour after midnight, almost immediately after the beginning. Yet somehow stars had already formed, galaxies assembled, radiation spread through space, and enough structure emerged for Webb to observe billions of years later. The young universe seems to have become complicated very quickly, and that realization unsettled some existing assumptions. Prior to Webb, many models predicted more gradual galaxy formation. Small primitive systems should slowly merge into larger galaxies over time. That still certainly happens. But Webb revealed something surprising. Large, luminous galaxies appeared earlier than expected. Not just JADES-GS-Z14-0 either. several unexpectedly bright ancient galaxies emerged from Webb observations, and astronomers began joking nervously that the telescope was breaking cosmology. Now, to be clear, cosmology itself is not collapsing dramatically into chaos, while scientists flee observatories clutching notebooks. The standard cosmological model still explains enormous amounts of observational evidence extremely successfully. But Webb's discovery suggests some details regarding early galaxy formation may require revision. And science progresses precisely through moments like these. Observations improve, unexpected evidence appears, theories adapt, human understanding grows slightly less incomplete. One particularly fascinating aspect of the discovery involves how normal the galaxy simultaneously appears and does not appear. On one hand, JADES-GS-Z14-0 is incredibly ancient and existed during a period very unlike the modern universe. On the other hand, it already resembles a recognizable galaxy rather than some completely alien structure. That continuity matters. It suggests the basic processes shaping galaxies today, gravity gathering matter, stars forming from collapsing gas clouds, radiation influencing surrounding environments, were already operating very early in cosmic history. The universe began building familiar structures surprisingly soon after the Big Bang. And perhaps there's something comforting in that. The cosmos did not remain chaotic forever. Patterns emerged. Order developed gradually from simplicity. Gravity patiently assembled structure out of near uniformity. Even during the earliest eras, the universe already carried hints of the galaxies, stars, and planets yet to come. Still, the discovery of JADES-GS-Z14-0 also reminds us how incomplete our perspective remains. Webb observes only part of the observable universe. Countless ancient galaxies likely remain unseen. Some may be even older or more massive. Others may exist beyond Webb's detection limits entirely. And because light travels at finite speed, there are regions of the universe forever inaccessible to observation. Their light simply has not had enough time to reach us since the Big Bang. Humanity observes only a cosmic horizon. Beyond it, more universe almost certainly exists, possibly endlessly. That idea can feel unsettling initially, but it can also feel strangely peaceful. The universe does not need to become fully known to be meaningful. Astronomy is not the story of humans conquering cosmic mystery completely. It is the story of gradually learning how much larger reality truly is, and every generation extends the horizon slightly farther. Webb extended it dramatically. The telescope allowed humanity to see ancient galaxies from near the dawn of cosmic history with astonishing clarity, and among those discoveries, JADES-GS-Z14-0 became one of the most important because it pushed directly against the boundaries of existing expectations. It revealed a young universe already producing substantial luminous structures astonishingly early. A cosmos becoming complex faster than anticipated. And perhaps most remarkable of all, the discovery emerged not through science fiction technology or imaginary physics, but through patience, engineering, mathematics, and careful observation. Human beings built a cold infrared telescope, launched it into deep space, aligned gold-coated mirrors with nanometer precision, collected ancient photons over long exposures, analysed stretched spectra, and uncovered evidence from nearly the beginning of time itself. That remains one of the great achievements of our species. Even now, while most people sleep beneath ordinary night skies, Webb continues drifting quietly near L2, collecting more ancient light, photon by photon, galaxy by galaxy. The telescope keeps peering backward into cosmic history, searching deeper into the darkness that existed before galaxies had names, and somewhere out there, perhaps even older structures still wait patiently for humanity to notice them. One of the strangest truths in astronomy is that telescopes do not really show us space, they show us time. At first glance, those two things sound interchangeable. After all, space and time are woven together into space-time according to relativity, and astronomers constantly measure both simultaneously. But emotionally, humans tend to think about telescopes as tools for observing distant places. In reality, they are historical instruments. Every time you look upward, you're seeing the past. Not metaphorically, literally. Moonlight reaching your eyes tonight left the moon about 1.3 seconds ago. Sunlight takes roughly 8 minutes to arrive at Earth. The nearest star beyond the Sun appears as it existed more than 4 years ago. And galaxies. Galaxies allow us to look millions or billions of years backward through cosmic history. Which means when Webb observes JADES-GS-Z 14-0, humanity is not seeing the galaxy as it exists now. We're seeing it as it existed around 13.5 billion years ago. That distinction matters enormously, because the galaxy almost certainly looks completely different today, assuming it still exists in recognizable form at all. Its stars have evolved. New generations of stars may have formed and died. Collisions and mergers may have reshaped it repeatedly. Entire regions may have transformed beyond recognition, but we cannot see any of that yet. The newer light simply has not arrived. And this is where astronomy becomes deeply strange in a wonderfully quiet way. The observable universe is not a snapshot of simultaneous events. It is a layered archive of different times. Nearby objects appear relatively recent. Distant objects appear ancient. The farther outward we look, the farther backward in time we observe. In a sense, the universe preserves its own history in light. And every telescope is essentially a machine for reading increasingly old chapters. Now, when astronomers say JADES-GS-Z 14-0 lies over 13.5 billion light-years away, people naturally imagine the galaxy sitting at that exact distance today. But cosmic expansion complicates matters, very significantly. Remember, the universe itself expands while light travels through it. That means galaxies continue moving farther apart during the journey of photons across space. So when the light from JADES-GS-Z 14-0 first began travelling toward us, the galaxy was much closer than it is now. Over billions of years, cosmic expansion stretched the intervening space enormously. Today, the galaxy's current distance is estimated to be vastly greater than 13.5 billion light-years. In fact, due to expansion, the present-day separation may exceed 30 billion light-years. Which sounds mildly impossible at first, because people understandably assume nothing should end up farther away than light could travel during the age of the universe. But again, expansion changes everything. Galaxies are not racing through static empty space faster than light in the ordinary sense. Instead, space itself expands between distant regions. It's an important distinction, and honestly one of the points where many people's brains politely excuse themselves for a brief walk. Still, the core idea remains beautiful. Ancient light reaching Webb today began its journey when the universe itself was extraordinarily young. The photons travelled continuously for over 13 billion years through expanding space-time. And only now do they arrive. That means every observation of JADES-GS-Z 14-0 is fundamentally an observation of cosmic history. Astronomers are not merely studying a distant galaxy. They are studying a very early stage in the evolution of the universe itself. Now, this ability to look backward through time is unique among sciences. Geologists reconstruct Earth's past using rocks and fossils. Biologists study evolution through genetics and ancient remains. Historians analyze records and artifacts. Astronomers, meanwhile, directly observe the past because light itself carries delayed information across space. The cosmos provides its own historical record automatically, and the farther away an object exists, the older the information becomes. This creates an astonishing situation where some distant galaxies appear younger than nearby stars. A nearby star might show us relatively recent conditions only decades old in light travel time. A distant galaxy may reveal an era billions of years earlier. The night sky is a mixture of different ages layered together simultaneously. Every point of light belongs to a different moment in cosmic history. And once you truly absorb that idea, the universe never quite looks the same again. Even ordinary stargazing changes emotionally. The stars above stop feeling immediate and present. Instead, they become messages crossing time. Some stars visible tonight may already be gone. Their light continues arriving anyway. Others may persist long after humanity disappears entirely. Light travels patiently regardless of whether anyone watches. Now, when Webb observed JADES-GS-Z14-0, astronomers were effectively peering toward the edge of what is currently observable. Not the edge of the universe itself. That distinction matters. As far as we know, the universe may extend vastly beyond what we can see, possibly infinitely far. But the observable universe represents the region from which light has had enough time to reach us since the Big Bang. Because the universe has a finite age, there exists a cosmic horizon beyond which information remains inaccessible. No telescope, regardless of power, can see beyond that horizon because the light simply has not arrived yet. This gives astronomy a strangely intimate relationship with time. Observation depends not only on distance, but on the age of the universe itself. Humanity can observe ancient galaxies only because their photons have finally completed journeys lasting billions of years. In a sense, the universe reveals itself gradually, patiently. Now, one reason JADES-GS-Z14-0 attracted so much attention is because observing galaxies this early helps astronomers study how quickly cosmic structure emerged after the Big Bang. Remember, the early universe initially lacked stars and galaxies entirely. During the cosmic dark ages, space remained mostly filled with hydrogen gas and invisible dark matter halos. Then gravity slowly gathered matter into denser regions until the first stars ignited. Eventually, primitive galaxies formed. By observing galaxies from different eras, astronomers can reconstruct this evolutionary process. It's a little like assembling a time-lapse video from separate photographs taken across billions of years. Nearby mature galaxies reveal later cosmic stages. Distant galaxies reveal earlier ones. The farther Webb looks, the younger the universe appears, and JADES-GS-Z14-0 belongs to an astonishingly early frame in that cosmic timeline. At only about 290 million years after the Big Bang, the galaxy existed during one of the earliest known periods of galaxy formation. This creates important constraints for cosmological models, because galaxies require ingredients. Gas must collapse gravitationally, stars must form, heavy elements begin accumulating, radiation alters surrounding intergalactic space. These processes need time, or at least scientists assume they did, yet JADES-GS-Z14-0 appears surprisingly luminous and developed very early, which suggests structure assembled rapidly, perhaps more rapidly than many models anticipated, and that raises fascinating possibilities. Maybe the first stars formed more efficiently, maybe gas cooled faster, maybe early dark matter halos collapse more aggressively, or perhaps feedback processes inside early galaxies behave differently than expected. Astronomy currently sits inside a thrilling period where observations from Webb continuously pressure test theoretical assumptions, and that's healthy for science. A theory surviving observational challenge becomes stronger. A theory requiring revision becomes more accurate. Either way, knowledge improves. Though admittedly, the universe occasionally improves knowledge by behaving in deeply inconvenient ways for existing equations. Now, another remarkable aspect of looking 13.5 billion years into the past involves scale itself. The human brain evolved to navigate forests, weather, social relationships, and occasionally suspicious noises in tall grass. It did not evolve to comfortably process billions of years. or distances measured in billions of light years, which is why cosmology often feels emotionally slippery. Numbers become so large they stop behaving intuitively. For example, when people hear 13.5 billion years, they often mentally compress it into very old. But there's a profound difference between 1,000,000 years and 1,000,000,000 years. 1,000,000 seconds equals roughly 11 days. 1,000,000,000 seconds equals over 31 years. Cosmic timescales operate at levels vastly beyond ordinary human intuition. And yet, remarkably, the universe still leaves observable evidence accessible to finite minds on one small planet. Humans can study the earliest galaxies despite existing incredibly late in cosmic history. That alone feels extraordinary. Because from a cosmic perspective, humanity arrived surprisingly recently. If the universe's history were compressed into a single calendar year, modern civilization would occupy only the final seconds before midnight on December 31st. Everything humans have ever built exists near the very end, and still, in those final seconds, one species learned how to detect ancient infrared photons from galaxies near the beginning. There's something quietly beautiful about that. Not triumphant exactly, more humbling. The universe spent billions of years evolving stars and galaxies before observers capable of understanding cosmic history appeared, and now, here we are. Tiny conscious creatures briefly awake inside a vast expanding cosmos, building telescopes and trying very hard to understand where everything came from, including ourselves. Because ultimately, studying galaxies like JADES-GS-Z 14-0 is not only about ancient light, it's about origins. The first galaxies shaped everything that followed. Inside early stars, heavier elements formed for the first time. Those elements later became planets, atmospheres, oceans, biology. Without early galaxy formation, Earth could never exist. Neither could humans. So when Webb observes ancient galaxies, humanity is indirectly observing the beginning of its own cosmic ancestry. Not personal ancestry. Cosmic ancestry. The earliest galaxies transformed a chemically simple universe into one capable of complexity, and that process eventually led through billions of years of stellar evolution to creatures who stay awake at night listening to stories about infrared telescopes. The continuity is remarkable. Now, there's another subtle consequence of observing such distant objects. When astronomers study galaxies from progressively earlier times, they also witness changes in the universe itself. The cosmos evolves. Young galaxies differ from mature galaxies. Star formation rates change over time. Chemical composition evolves. The large-scale structure of the universe develops gradually. Looking far away means observing a younger cosmos with different conditions, and Webb's observation suggests the early universe may have matured faster than expected. Galaxies like JADES-GS-Z 14-0 already exhibit substantial star formation surprisingly soon after the Big Bang. This hints that cosmic evolution during the first few 100 million years may have been more dynamic than many models predicted. The young universe was busy, very busy. Gravity assembled structure aggressively. Stars ignited rapidly. Radiation flooded intergalactic space. Galaxies emerged from darkness much sooner than anticipated. And perhaps the most astonishing part is that we can know any of this at all. Think about what had to happen for humanity to observe JADES-GS-Z 14-0. The universe needed to create stable physical laws. Stars had to forge heavy elements. Planets had to form. Life had to emerge. Intelligence had to evolve. Civilization had to develop mathematics, optics, engineering, cryogenics, rocketry, detector technology, orbital mechanics, spectroscopy, and international scientific collaboration. Then humans needed to launch a giant infrared telescope into deep space and align its mirrors with nanometer precision. All so ancient photons from near the beginning of cosmic history could finally be detected. It's an astonishing chain of events, and the photons themselves simply travelled the entire time without interruption. No urgency, no awareness, no destination in mind. Light from JADES-GS-Z 14-0 began its journey before the Milky Way looked familiar, before the Sun existed, before Earth formed, and only now has the universe produced observers capable of understanding what those photons represent. That realization changes how one thinks about the night sky. The stars stop feeling static. Everything becomes process, history, motion, evolution unfolding across immense timescales. Even darkness gains depth, because empty-looking space may contain ancient photons still travelling toward future observers billions of years from now. Some light crossing the universe tonight may eventually illuminate worlds and civilizations not yet born. The cosmos is full of delayed messages, and telescopes like Webb allow humanity to read some of the oldest ones ever received. Still, for all the staggering distances and timescales involved, JADES-GS-Z 14-0 remains only one galaxy among countless others. The early universe likely contained many ancient systems still waiting to be discovered. Some may prove even older, some may challenge cosmology further, and somewhere beyond the observable horizon, regions of the universe remain forever unseen, their light still travelling, their histories inaccessible. The cosmos always remains partly hidden. Perhaps that is fitting. Mystery survives no matter how far telescopes reach. But with Webb, humanity has moved closer than ever before to witnessing the first great structures emerging from cosmic darkness. Astronomers become nervous when the universe behaves too efficiently, not because scientists dislike discovery, quite the opposite. Most astronomers secretly hope nature will reveal something unexpected during their careers. Entire scientific fields advance through surprises. New observations force better theories. Better theories lead to deeper understanding. But there is a particular kind of surprise that creates a very specific mood in astronomy. The kind where researchers stare at data for a long time and quietly say, "That seems early." JADES-GS-Z 14-0 produced exactly that reaction. Because according to many earlier models of cosmic evolution, galaxies this bright and developed should not have existed only 290 million years after the Big Bang. At least not easily, and certainly not comfortably. The problem was not that galaxies existed at all during this period. Astronomers already expected some early structures to form relatively soon, after the first stars ignited. The problem was scale, brightness, complexity. JADES-GS-Z 14-0 appeared more substantial than many scientists anticipated for such an early cosmic era, which meant one of two things. Either astronomers had underestimated how quickly galaxies can form, or the young universe was operating differently than expected. Possibly both. Now, to understand why this became such a fascinating issue, we need to talk a little about how galaxies actually form. And despite the enormous scales involved, the basic ingredients are surprisingly simple. Gravity, gas, time. That's really the foundation. After the Big Bang, matter spread through expanding space with slight density variations inherited from the early universe. Dark matter halos formed first, creating gravitational wells that attracted ordinary gas, mostly hydrogen and helium. Gas clouds fell inward, density increased, temperatures rose, eventually stars ignited. Over time, stars grouped together into primitive galaxies. Those galaxies merged with others, accumulated more gas, formed additional stars, and gradually evolved into the enormous structures we see today. At least, that was the general picture. And for years, simulations suggested this process should unfold somewhat gradually. The earliest galaxies should be relatively small and faint, because the universe simply had not existed long enough for large systems to assemble efficiently. Imagine trying to build a city immediately after inventing bricks. Technically possible to start, more difficult to finish quickly. The young universe faced similar constraints. Stars need time to form. Supernovae need time to enrich galaxies with heavier elements. Gas needs time to cool and collapse into denser structures. Galaxies need time to merge and grow, or at least that was the assumption. Then Webb arrived, and suddenly the early universe looked far busier than expected. Not empty, not primitive, busy. Galaxies appeared brighter, more numerous, more developed. Researchers began finding ancient systems surprisingly soon after the Big Bang. Some jokingly referred to this as the too big, too early problem, which sounds slightly like a complaint from someone ordering furniture online but actually refers to one of the most interesting tensions in modern cosmology. JADES-GS-Z 14-0 became one of the strongest examples because of its extraordinary redshift and apparent luminosity. The galaxy existed during a period when the cosmos itself was still very young, and yet it already emitted enough light for Webb to detect across over 13 billion years of expanding space. That suggests significant star formation was already underway, possibly involving millions or even billions of stars, very early. Now, this does not mean the standard cosmological model is collapsing dramatically into confusion, while physicists run through hallways carrying flaming equations. The overall framework of cosmology remains extremely successful. The Big Bang model explains enormous amounts of observational evidence remarkably well. Cosmic expansion, the cosmic microwave background, large-scale structure, nucleosynthesis, all align strongly with modern cosmological theory. But details matter, especially details involving early galaxy formation. And Webb's discovery suggests some assumptions about the timing and efficiency of those processes may need adjustment. One possibility is that stars formed much more efficiently in the young universe than expected. Perhaps gas collapsed into stars at unusually high rates during the earliest cosmic epochs. If primordial gas clouds converted matter into stars rapidly, galaxies could brighten surprisingly fast. Another possibility involves the first stars themselves. Remember the hypothetical population 3 stars from earlier. These first-generation stars may have been extremely massive, hot, and luminous. If the early universe produced large numbers of gigantic stars quickly, young galaxies could appear brighter than previously predicted even without enormous masses. A few very massive stars can produce extraordinary amounts of light, though admittedly they also behave like cosmic fuel addicts, burning through nuclear material at alarming speeds. Still, intense early star formation could help explain Webb's observations. There's also the role of dark matter halos. Galaxies form inside these invisible gravitational structures, and the timing of halo formation strongly influences cosmic evolution. If dark matter halos assembled earlier or more efficiently than models predicted, galaxies might emerge faster as well. Now, dark matter itself remains deeply mysterious. Astronomers know it exists because gravitational observations demand additional unseen mass. Galaxies rotate too quickly. Clusters remain bound too strongly. Gravitational lensing reveals invisible matter distributions, but nobody knows exactly what dark matter particles are, which means the universe is effectively saying, most matter exists in a form you still don't understand, but please continue your calculations anyway. A wonderfully cosmic sort of confidence-building exercise, so it's entirely possible that early dark matter behavior contributed to faster galaxy formation. Or perhaps cooling mechanisms in the young universe operated differently than expected. Gas clouds must lose energy efficiently to collapse into stars. Heavy elements help cooling in modern galaxies, but the early universe lacked those elements almost entirely. Scientists expected this limitation to slow star formation somewhat. Yet Webb suggests galaxies still assembled rapidly. Maybe primordial gas behaved more dynamically. Maybe turbulence played a larger role. Maybe feedback processes from early stars altered surrounding environments in unexpected ways. Astronomers are actively investigating all these possibilities right now. And that's one of the exciting things about science in real time. The answers are not fully settled yet. Humanity currently exists inside the discovery process itself. Now, another fascinating aspect of JADES-GS-Z 14-0 is what it implies about cosmic reionization. During the cosmic dark ages, much of the universe contained neutral hydrogen gas. This gas absorbed ultraviolet light strongly, making intergalactic space relatively opaque to certain radiation. Then the first stars and galaxies began ionizing surrounding hydrogen. Little bubbles of ionized gas expanded outward. Eventually these bubbles overlapped until much of intergalactic space became ionized again. This process, called reionization, fundamentally transformed the universe. But astronomers still debate exactly how quickly it occurred and which objects contributed most strongly. Bright early galaxies like JADES-GS-Z 14-0 may have played an important role. If substantial galaxies existed earlier than expected, they could have accelerated reionization significantly. In other words, these ancient systems may have reshaped the state of the universe itself remarkably soon after the Big Bang. Tiny distant smudges in Webb images suddenly become cosmologically important, and perhaps emotionally important too, because there is something astonishing about realizing the universe organized itself into luminous structures so quickly. The cosmos did not remain dark and simple for very long. Gravity began building complexity almost immediately. Stars ignited, galaxies assembled, radiation transformed intergalactic space. The universe became active very early, almost eager, though cosmic eagerness still unfolds across millions of years, which remains slightly slower than most people checking package delivery updates online. Still, JADES-GS-Z 14-0 challenges a deeply human instinct. We tend to imagine complexity emerging slowly and cautiously, yet the early universe may have evolved with surprising speed. Given the right conditions, structure appears rapidly. And perhaps that idea extends beyond cosmology in interesting ways. The universe did not require perfection before beginning creation. Tiny fluctuations became galaxies. Simple hydrogen became stars. Early stars produced heavier elements. Eventually planets formed. Then biology. Then consciousness. Then telescopes observing ancient galaxies from one small world orbiting one ordinary star. The chain of events unfolded surprisingly quickly once gravity and time began working together. Now some astronomers caution against overreacting too dramatically to Webb's discoveries, and that caution is reasonable. Observations of extremely distant galaxies remain challenging. Measurements carry uncertainties. Theoretical models continue improving. Simulations become more sophisticated over time. Sometimes apparent tensions weaken as understanding improves. Other times, tension deepen and force major revisions. Science does not know yet which outcome awaits here, but either possibility is valuable. If existing models adapt successfully, cosmology becomes more refined. If major revisions prove necessary, humanity learns something profoundly new about the early universe. Discovery wins either way, and Webb continues collecting data constantly. That's important because JADES-GS-Z 14-0 is not alone anymore. Additional high redshift galaxies continue emerging from Webb observations. Some appear surprisingly bright. Others exhibit unexpected properties. Together they paint a picture of an early universe, potentially richer and more active than anticipated. The cosmic dawn may have arrived faster than expected, and future observations may reveal even older galaxies still waiting in the darkness. Imagine that for a moment. Right now, somewhere beyond Webb's current observations, additional ancient photons continue travelling toward us from galaxies humanity has not discovered yet. Perhaps some formed even earlier. Perhaps some challenge current theories further. Those photons are already on their way. The universe simply has not delivered them to us yet. There's something wonderfully calming about that idea. Reality contains information far older and stranger than human knowledge currently includes. The cosmos remains partly hidden, not because it refuses to exist, but because light itself requires time, and time the universe has in abundance. Now, one subtle emotional effect of discoveries like JADES-GS-Z 14-0 is how they reshape humanity's sense of cosmic history. Before Webb, many people imagined the early universe as relatively barren for long periods, a slow, gradual climb towards structure. Instead, the picture emerging now feels more dynamic. The universe became creative quickly. The first galaxies may have assembled with astonishing efficiency. Complexity emerged almost immediately after conditions allowed it, and perhaps there is something hopeful in that, not in a sentimental sense, more in a structural sense. Given matter, gravity, and time, the universe naturally produces stars and galaxies. Complexity emerges from simplicity repeatedly across cosmic scales. Order appears, patterns form, light eventually fills darkness. That process began very early, earlier than expected. Still, despite all the excitement surrounding JADES-GS-Z 14-0, astronomers remain careful not to oversimplify what Webb has found. The galaxy is not a fully mature spiral like the Milky Way. It belongs to a vastly different cosmic era. Conditions in the young universe were harsher, denser, and more chaotic. Early galaxies likely experienced intense bursts of star formation, violent radiation environments, frequent mergers, and rapid evolution. The universe near the cosmic dawn was turbulent, but turbulence does not prevent beauty. Sometimes it creates it. Modern galaxies themselves emerge from billions of years of collisions, mergers, explosions, and gravitational interactions. Even the Milky Way continues absorbing smaller galaxies today. Cosmic history is not calm, it is productive, and JADES-GS-Z 14-0 reminds us just how productive the early universe may already have been, astonishingly soon after the beginning. Now Webb continues looking farther back. Longer exposures, deeper surveys, more ancient light. Astronomers keep pushing toward earlier and earlier cosmic epochs, searching for the first galaxies, the first stars, perhaps eventually even indirect evidence from the transition out of the cosmic dark ages themselves. And each discovery forces humanity to reconsider its assumptions about how quickly the universe became recognizable. Because apparently, the cosmos wasted very little time turning darkness into light. Before there were planets, before there were galaxies like the Milky Way, before there were trees or oceans or creatures arguing politely with alarm clocks every morning, the universe had to invent stars. Not ordinary stars at first. The earliest stars may have been enormous beyond anything comfortably familiar. Brilliant, violent, short-lived, and absolutely essential. Because without them, the universe would likely remain a chemically boring place filled mostly with hydrogen and helium drifting through darkness forever. The first giant stars changed everything. To understand why, we need to return once again to the young universe shortly after the cosmic dark ages began ending. At this stage, the cosmos looked very different from the modern one. There were no mature galaxies yet, no planets, no rocky worlds, no heavy elements in meaningful quantities. The universe remained chemically primitive. Hydrogen dominated almost everything. Helium came second. That was more or less the entire recipe. And while hydrogen and helium are perfectly respectable elements, they are not particularly good at building complicated things by themselves. You cannot construct mountains, oceans, forests, nervous systems, or sleepy podcast listeners using only hydrogen and helium. For complexity to emerge, the universe needed stellar furnaces. It needed stars capable of forging heavier elements through nuclear fusion, and the first stars may have formed under conditions unlike anything common today. Now, modern stars usually form inside giant molecular clouds enriched by previous generations of stellar evolution. Those clouds contain heavier elements like carbon, oxygen, silicon, and iron. Astronomers refer to all elements heavier than helium as metals, which occasionally causes confusion because oxygen does not exactly resemble a bicycle chain. Still, in astronomy, metals simply means heavier elements. These elements matter enormously because they help gas cool efficiently. Cooling is important during star formation. A collapsing gas cloud heats up as gravity compresses it. If the gas cannot cool effectively, pressure resists further collapse. Heavy elements and dust allow modern gas clouds to radiate energy away more efficiently, helping fragmentation occur. This fragmentation produces many smaller stars. But the first stars formed before those heavier elements existed. The early universe lacked stellar pollution. No previous generations of stars had exploded yet to enrich interstellar space. That changed everything about how primordial gas behaved. Without efficient cooling, collapsing gas clouds in the young universe may have formed much larger stars than modern clouds typically do. And when astronomers say larger, they mean genuinely enormous. Some theoretical models suggest the first stars may have reached masses hundreds of times greater than the Sun. Imagine a star so massive that our Sun, itself already capable of swallowing over 1 million Earths by volume, would seem modest in comparison. These first stars were cosmic giants, and giant stars behave dramatically. Now, despite their size, the earlier stars likely formed through the same fundamental process governing star formation today. Gravity gathered gas into increasingly dense regions. As hydrogen accumulated, pressure and temperature inside the collapsing core rose steadily. Eventually, conditions became extreme enough for nuclear fusion to ignite. Hydrogen nuclei fused into helium. Energy erupted outward. A star was born. Fusion creates an extraordinary balance inside stars. Gravity continuously pulls matter inward, while radiation pressure from fusion pushes outward. The result becomes a stable, glowing sphere. At least for a while. But giant stars consume fuel at astonishing rates. There's a strange rule in astrophysics that surprises many people initially. Larger stars live shorter lives. At first, that seems backward. People naturally assume larger objects should last longer, but giant stars burn fuel enormously faster because their cores reach much higher temperatures and pressures. A massive star may contain vastly more hydrogen than the Sun, yet it consumes that fuel with extraordinary intensity. Like someone buying a gigantic candle and then setting it directly inside a hurricane. The Sun will likely survive around 10 billion years total. Some early giant stars may have lived only a few million years. Cosmically speaking, that is astonishingly brief. But during those short violent lives, they transformed the universe permanently. Now, one reason astronomers believe the first stars were probably extremely massive involves the absence of metals in the early universe. Modern stellar populations contain many smaller stars because enriched gas clouds fragment efficiently during collapse. Primordial gas behaved differently. Simulations suggest large, dense clumps may have formed more easily, producing giant stars with relatively little fragmentation. Of course, observing these first stars directly remains extremely difficult, possibly impossible with current technology. No confirmed population 3 star has ever been observed. That's because the earlier stars likely died billions of years ago, and they died spectacularly. Massive stars end their lives violently because fusion eventually reaches limits. Hydrogen fuses into helium, helium into heavier elements. Progressively more complex fusion occurs inside stellar cores, but eventually fusion can no longer generate sufficient outward pressure. Gravity wins. the core collapses catastrophically, and the resulting explosion becomes a supernova. Some of the earliest giant stars may have produced especially extreme explosions called pair instability supernova, events so energetic they could completely destroy the star without leaving behind a neutron star or black hole remnant. Others likely collapsed directly into black holes. Either way, these stars unleashed enormous amounts of energy and newly forged elements into surrounding space. And this is where the story becomes deeply important for everything that followed. The first stars manufactured the universe's first heavy elements: carbon, oxygen, silicon, iron, elements required for rocky planets, atmospheres, chemistry, and eventually biology. Before stars existed, the universe lacked almost all the materials necessary for complex structures. The first stars changed that forever. They were cosmic alchemists, factories of complexity. And perhaps one of the most astonishing facts in astronomy is that every atom heavier than hydrogen in your body originated inside stars. Your calcium, your oxygen, your iron, your carbon, all forged through stellar fusion somewhere across cosmic history. Not metaphorically, literally. Human beings are assembled from recycled stellar material, which means the story of the first giant stars is also quietly the beginning of your own material ancestry. There is something wonderfully strange about that. Now, another crucial effect of the first stars involved radiation. These stars were incredibly hot and luminous. They emitted intense ultraviolet radiation capable of ionizing surrounding hydrogen gas. Remember, after recombination, the universe largely contained neutral hydrogen. Then the first stars switched on. Their radiation blasted through nearby space, creating expanding bubbles of ionized gas around them. Eventually larger structures formed. Primitive galaxies containing many stars emerged. More radiation flooded the universe. Little ionized regions overlapped and expanded, until much of intergalactic space became ionized once again. This process, cosmic reionization, fundamentally transformed the universe. The first stars helped end the cosmic dark ages. They literally illuminated the cosmos. And they likely did so earlier than scientists once expected. That's one reason galaxies like JADES-GS-Z 14-0 matter so much. Its existence suggests intense star formation was already occurring only a few 100 million years after the Big Bang. To produce substantial luminosity so early, the universe must already have formed large populations of stars, possibly giant stars, possibly very efficiently, and perhaps sooner than earlier cosmological models predicted. Webb's observations hint that the cosmic dawn arrived rapidly. The first stars may have ignited across the universe surprisingly quickly once conditions allowed gravitational collapse. And once those first stars appeared, everything accelerated. Heavy elements enriched surrounding gas. Cooling improved. More stars formed. Galaxies assembled faster. Complexity spread. The universe became productive. Very productive. It's almost as though the cosmos spent millions of years gathering ingredients quietly during the Dark Ages, then suddenly discovered nuclear fusion and became wildly enthusiastic about chemistry. Now, one fascinating possibility is that some of the earliest giant stars collapsed into black holes massive enough to seed future supermassive black holes. This matters because Webb has also discovered evidence for surprisingly massive black holes in the early universe, and astronomers are still trying to understand how black holes grew so rapidly after the Big Bang. Perhaps giant population 3 stars helped provide the initial building blocks. A huge primordial star collapses, a black hole forms, matter accumulates rapidly, galaxies merge, and eventually gigantic black holes emerge at galactic centers, including the supermassive black hole lurking quietly at the center of the Milky Way today. Again, cosmic history reveals continuity everywhere. The earliest stars influenced nearly every later stage of evolution. Galaxies, chemistry, planets, black holes, potentially life itself, all linked. Now, despite their importance, the first giant stars were probably lonely compared to modern stellar environments. Today, the universe contains hundreds of billions of galaxies filled with stars, but the first stars appeared in relative isolation inside tiny, primitive structures. Imagine one enormous, blazing star igniting in a vast sea of darkness, where no stars had ever existed before, no constellations yet, no galaxies filling the sky, just one giant stellar furnace switching on for the first time in cosmic history. There's something emotionally powerful about that image, the universe's first sunrise. And after millions of years of darkness, those first lights must have transformed surrounding space dramatically. Radiation spread outward, hydrogen ionized, temperature changed. Future star formation became easier in enriched regions. The cosmos gradually shifted from simplicity toward complexity. One generation of stars enabling the next. Astronomy often works that way. Everything builds on what came before. Stars create heavier elements. Those elements create planets. Planets create environments where chemistry can become increasingly complex. Eventually somewhere, at least once that we know of, biology appears. Then consciousness. Then telescopes observing ancient galaxies from billions of years later. The continuity remains astonishing. Now there's another reason giant stars matter. They are extraordinarily luminous. A single, very massive star can outshine vast populations of smaller stars. This means early galaxies containing giant stars could appear surprisingly bright, even if their total mass remained relatively modest. And that may help explain some of Webb's discoveries. Galaxies like JADES-GS-Z14-0 might contain stellar populations dominated by hot, massive stars producing intense ultraviolet radiation. In other words, part of the reason these galaxies seem unexpectedly luminous may be because the early universe favoured especially bright stellar populations. The cosmos may have glowed fiercely during its youth. Astronomers are actively studying this possibility now using Webb spectroscopy and theoretical modelling, and once again the answers remain incomplete, which is exciting. Humanity currently lives during a period when the first stars and galaxies are transitioning from theoretical speculation into observable science. For decades, astronomers could only model these epochs indirectly. Now Webb is beginning to reveal them directly, and the picture emerging feels dynamic, violent, bright. The young universe appears less hesitant than many expected. Now, giant stars also teach us something quietly humbling about scale. Human beings instinctively associate longevity with importance. Ancient trees feel majestic because they endure centuries. Mountains feel powerful because they outlast civilizations. But the universe often behaves differently. Some of the most influential stars in cosmic history lived only briefly, a few million years. Tiny flashes compared to the sun's lifespan. And yet those brief lives transformed everything that followed. Without them, later generations of stars could not form properly. Planets could not exist. Heavy elements would remain absent. Complex chemistry might never emerge. The first giant stars changed the trajectory of the universe permanently despite their short lives. And perhaps that's one of the calming things about cosmology. Duration alone does not determine significance. Now, somewhere in the observable universe tonight, giant stars continue forming. Not true population 3 stars perhaps, those likely vanished long ago, but enormous luminous stars still ignite inside dense star-forming regions across galaxies. They still fuse hydrogen into heavier elements, still sculpt surrounding gas with radiation and stellar winds, still explode dramatically when fusion ends. The universe continues recycling matter endlessly through generations of stars. Ancient stellar ashes become new stars. New stars produce new elements. Planets emerge. Galaxies evolve. everything remains connected through cycles unfolding across billions of years. And somewhere deep in the past, near the dawn of cosmic history, the first giant stars began that process. They switched on inside darkness no star had ever illuminated before. Their radiation spread through the young universe. Their explosions forged the first heavy elements, and their brief, brilliant lives helped create the conditions necessary for every galaxy, planet, ocean, and living creature that would eventually follow. For a long time, astronomers believed the early universe should be relatively modest. Not empty exactly, not lifeless in a cosmic sense, but gradual, careful, slow to organize itself. The reasoning seemed sensible. After the Big Bang, matter spread through expanding space with only tiny density fluctuations. Gravity then needed time to gather gas into dark matter halos, cool that gas, ignite stars, assemble primitive galaxies, and eventually grow larger structures through mergers and continued star formation. The process sounded orderly, reasonable, physics approved. Then the James Webb Space Telescope began showing astronomers the actual early universe, and the universe responded by saying something very close to yes about your timelines, because Webb kept finding galaxies that looked unexpectedly mature for their age. Not impossible necessarily, but uncomfortable, like discovering a fully functioning city in what should still be a construction site with one lonely traffic cone and a confused bulldozer operator wondering where everyone went. JADES-GS-Z 14-0 became one of the strongest examples of this tension. The galaxy existed only about 290 million years after the Big Bang. Cosmically speaking, that is astonishingly early, and yet it already appeared bright enough to imply substantial star formation was underway, which forced astronomers into an awkward but exciting situation. Either the young universe built galaxies faster than predicted, or some assumptions inside existing models required revision, possibly several assumptions at once. Now, it's important to understand that modern cosmology is not failing catastrophically here. Scientists not standing beside collapsing chalkboards while equations burst into flames around them. The standard cosmological model still explains enormous amounts of observational evidence extraordinarily well, but Webb revealed that the earliest epochs of galaxy formation may have been far more active and efficient than many researchers anticipated. The cosmic dawn seems to have arrived quickly, very quickly, and that raises one of the most fascinating questions in astronomy today. How did early galaxies grow so fast? Now, one possible answer involves star formation efficiency. Galaxies shine because stars shine. The brighter a galaxy appears, generally speaking, the more active star formation may be occurring inside it, and the young universe may have converted gas into stars far more aggressively than expected. Remember, the early cosmos contained enormous reservoirs of hydrogen and helium gas. Once gravity pulled sufficient matter into dark matter halos, collapse could begin. Perhaps those collapses happened with remarkable efficiency. Maybe primordial gas clouds fragmented differently. Maybe giant stars formed rapidly and in large numbers. Maybe radiation feedback behaved differently than models predicted. Astronomers are investigating all of these possibilities, and this is one of the thrilling things about Webb observations. They are forcing researchers to revisit assumptions that previously seemed fairly comfortable. Now, another factor involves dark matter halos themselves. Galaxies form inside invisible gravitational structures created by dark matter. Ordinary gas falls into these halos, eventually cooling and forming stars. The timing of halo formation therefore strongly influences how quickly galaxies can emerge. If early dark matter halos assembled faster or became denser than expected, galaxy growth could accelerate dramatically. And since dark matter remains mysterious, there's still room for surprises. Astronomers know dark matter exists because gravitational effects demand it. Galaxies rotate too rapidly for visible matter alone to explain. Clusters remain gravitationally bound more strongly than ordinary matter allows. Gravitational lensing reveals invisible mass distributions across the cosmos, but nobody knows exactly what dark matter particles actually are, which means humanity is effectively trying to explain cosmic structure while missing most of the matter involved. A wonderfully ambitious approach, really. Still, even without fully understanding dark matter itself, researchers can model its gravitational effects remarkably well, and Webb's discoveries suggest those early structures may have become productive sooner than expected. Now, another possibility concerns cooling in primordial gas clouds. This becomes slightly technical, but it matters enormously. Gas must cool effectively to collapse into dense star-forming regions. In modern galaxies, heavy elements and dust help radiate away heat, encouraging fragmentation and star formation. But the early universe lacked heavy elements almost entirely. That initially led many scientists to assume star formation might proceed somewhat slowly. Yet perhaps primordial gas cooled more efficiently through alternative mechanisms than previously thought. Hydrogen molecules, turbulence, and gravitational interactions may have helped accelerate collapse under certain conditions. If so, the first galaxies could begin producing stars rapidly, despite the chemically primitive environment. And once the first stars formed, everything changed quickly. Supernova explosions enriched surrounding gas with heavier elements. Cooling improved. Additional star formation accelerated. Galaxy growth became easier. The universe may have experienced a kind of runaway complexity effect during its youth. One generation of stars enabled the next generation to form more efficiently. And suddenly galaxies emerged surprisingly early. Now mergers also likely played an enormous role. The young universe was much denser than today. Galaxies existed closer together. Collisions and mergers occurred frequently. Small systems combined into larger ones rapidly. This hierarchical assembly process remains central to galaxy evolution models, but Webb suggests it may have happened aggressively during the earliest cosmic epochs. The universe did not politely wait billions of years before beginning large-scale structure formation. It got busy almost immediately, and perhaps that should not surprise us too much. Gravity is relentless. Give matter even slight density variations and enough time, and structure naturally emerges. Clouds become stars, stars gather into galaxies, galaxies merge into clusters. The cosmos builds complexity automatically through physical law. Still, the speed of early galaxy growth revealed by Webb feels startling, because humans instinctively imagine ancient epochs as primitive and undeveloped. We picture the young universe as sparse, empty, waiting. Instead, the emerging picture feels energetic, crowded, productive. By the time JADES-GS-Z14-0 emitted the light Webb detected, the universe may already have contained many actively evolving galaxies. And that realization changes how we think about cosmic history itself. The transition from darkness to structure appears to have happened rapidly. Now, one especially interesting aspect of these discoveries involves luminosity. Brightness matters because astronomers infer physical properties from light. If a galaxy appears extremely luminous very early, it suggests either intense star formation, very massive stars, active black holes, or some combination of these, and some early Webb galaxies appear surprisingly bright indeed, brighter than many simulations predicted, which means something in the early universe produced enormous amounts of energy quickly. One possibility is that the first generations of stars were unusually massive and hot. Remember the hypothetical population 3 stars? These primordial stars may have reached enormous masses due to the lack of heavy elements in the early universe. Massive stars emit tremendous ultraviolet radiation. Even relatively small galaxies dominated by giant stars could therefore appear extremely luminous. So perhaps early galaxies looked brighter not necessarily because they contained enormous masses, but because their stellar populations differ dramatically from modern galaxies. The young universe may have favoured blazing stellar giants, and those stars would profoundly influence surrounding environments. Radiation ionised nearby hydrogen. Supernova explosions enriched gas chemically. Black holes formed from stellar collapse. Everything evolved quickly. The cosmic dawn may have resembled a period of explosive creativity. Now there's another subtle factor here. Astronomers observe galaxies through light that has travelled across billions of years. That means measurements always involve interpretation. Researchers estimate stellar masses, star formation rates, chemical composition, and distances using models based on observed spectra and brightness. As observations improve, those estimates evolve, so some tensions between Webb discoveries and earlier models may soften over time as scientists refine interpretations. Others may deepen. That's normal. Science is not a finished static collection of perfect answers. It's a continuous process of revision and refinement, and astronomy especially operates at the edge of human perception. Researchers are trying to reconstruct ancient cosmic history using faint infrared photons stretched across expanding space for billions of years. The fact that this works at all remains astonishing. Now, one of the calming things about this entire situation is how naturally the universe creates complexity once conditions permit it. Humans often think of galaxies as extraordinary rare structures, and in a sense they are, but the universe seems remarkably good at making them. Give matter gravity and time, and galaxies emerge, not eventually in some distant, hesitant future. Quickly, perhaps very quickly. The cosmos may be fundamentally efficient at producing structure, and there is something strangely reassuring about that idea. The early universe did not remain dark forever. It organised itself. Stars formed, galaxies assembled, light spread through space, complexity appeared almost immediately once physical conditions allowed it. Now, Webb's discoveries also influence our understanding of reionization. Remember, the early universe after recombination contained large amounts of neutral hydrogen gas. Then radiation from the first stars and galaxies ionized much of intergalactic space. Bright early galaxies could contribute significantly to this process. If substantial galaxies already existed by Redshift 14, they may have helped reionize the universe sooner and more efficiently than expected. Tiny distant galaxies shaped the large-scale state of the cosmos itself, and that realization is wonderfully humbling. Massive cosmic transitions depended on the collective behavior of early stars and galaxies emerging from darkness. Everything influenced everything else. Radiation altered intergalactic gas. Gas influenced future star formation. Galaxies merged. Black holes grew. The universe evolved through interconnected feedback processes across enormous scales, and all of this happened astonishingly early. Now there's also a philosophical side to Webb's discoveries that people sometimes overlook. For centuries, humans imagined the distant past as simpler and emptier than the present. In many ways that's true, but Webb reveals that complexity arrived very quickly after the Big Bang. The cosmos wasted little time building structure. Perhaps complexity is not rare under the right conditions. Perhaps the universe naturally organizes matter into increasingly intricate forms whenever physical law allows it. Stars, galaxies, planets, chemistry, possibly life, again and again. And maybe that's one reason discoveries like JADES-GS-14-Z 14-0 feel emotionally important beyond pure science. They suggest the universe became vibrant and active remarkably early. Darkness did not last forever. The first light switched on quickly. Now, future observations may complicate this picture further. Webb continues detecting ancient galaxies. Some may prove even older. Others may reveal surprising chemical signatures or black hole activity. Future telescopes may push farther still, perhaps toward the first stars themselves. And every new observation refines humanity's understanding of cosmic evolution. astronomy advances through exactly this kind of dialogue between theory and observation. Scientists propose models. The universe responds with evidence. Researchers revise understanding. Then the universe reveals something even stranger. It's a wonderfully ongoing process. And right now, humanity exists during one of those exciting moments where the observable horizon is expanding dramatically. Before Webb, the first few 100 million years after the Big Bang remained largely mysterious. Now ancient galaxies emerge from the darkness regularly. Researchers are beginning to study the cosmic dawn directly rather than purely through theory, and the universe is proving more energetic than expected, more productive, more willing to create large luminous structures very early, which means somewhere in the darkness beyond current observations, additional ancient galaxies almost certainly still wait. Their light continues travelling toward us now, patiently crossing expanding space. Some photons from galaxies not yet discovered may already be approaching Webb at this very moment. The telescope simply hasn't collected them yet, and perhaps among those future observations lie even greater surprises about how quickly the universe learned to build itself. When people imagine the early universe, they often picture something peaceful. Quiet darkness, a few scattered stars, gentle cosmic beginnings unfolding slowly beneath calm ancient skies. But the real young universe was far less polite than that. It was violent. Not violent in a malicious sense, of course. The universe does not wake up each morning deciding to cause trouble for astronomers specifically, though sometimes it feels suspiciously close. Rather, the early cosmos was violent because enormous amounts of matter and energy were interacting inside a much denser environment than the modern universe. Galaxies collided constantly, stars exploded frequently, radiation flooded through intergalactic space, black holes consumed matter aggressively. The cosmic dawn was not calm. It was chaotic construction on unimaginable scales, and galaxies like JADES-GS-Z14-0 existed directly inside that turbulence. Now, one of the most important things to understand about the early universe is that everything was closer together. The universe has been expanding for 13.8 billion years, which means that long ago distances between galaxies were much smaller. Imagine watching raisins inside rising bread dough. As the dough expands, the raisins move farther apart from one another. Reverse the process and the raisins become increasingly crowded together. Cosmic expansion works similarly. In the young universe, galaxies occupied a denser environment that naturally increased the frequency of gravitational interactions and collisions. Modern galaxies often drift through enormous stretches of relatively empty space before major mergers occur. The early cosmos offered far less personal space. Galaxies pulled on one another constantly. Small systems merged into larger systems repeatedly. Matter flowed through cosmic structures rapidly, and this process helped galaxies grow astonishingly fast, including galaxies that perhaps should not have become so substantial, so early according to previous expectations. Now, when people hear the word collision, they sometimes imagine stars smashing directly into one another like celestial billiard balls. In reality, galaxy collisions behave differently. Galaxies mostly consist of empty space. Even during mergers, individual stars rarely collide directly because distances between stars remain enormous compared to their sizes. Instead, galaxies pass through each other gravitationally. Gas clouds compress, orbits distort, star formation erupts, matter redistributes. Entire galactic structures become reshaped. The process is chaotic but productive. In fact, galaxy mergers often trigger intense bursts of star formation. When giant gas clouds collide and compress, gravity drives rapid stellar birth. And in the early universe, where mergers occurred frequently, galaxies may have experienced near-continuous episodes of violent star formation. This could help explain why Webb observes surprisingly bright galaxies during very early cosmic epochs. The young universe may have functioned almost like a cosmic pressure cooker for galaxy growth. Everything interacted. Everything evolved rapidly, and nothing stayed stable for very long. Now radiation also played a profound role during this era. The first generations of stars were probably enormous and extremely hot. Massive stars emit tremendous ultraviolet radiation capable of ionizing surrounding hydrogen gas. As early stars ignited across primitive galaxies, ultraviolet light flooded nearby space. This radiation transformed the state of the universe itself. Remember, after recombination, most intergalactic hydrogen existed in neutral form. Then the first stars and galaxies began reionizing the cosmos. Little bubbles of ionized gas expanded outward around luminous regions. Eventually these bubbles overlapped until much of intergalactic space became ionized once again. But this was not a smooth or gentle process. The early universe resembled a patchwork of dark neutral regions mixed with expanding ionized zones surrounding galaxies. Radiation sculpted the cosmos unevenly. Some regions became transparent earlier than others. Some galaxies may have remained buried inside neutral hydrogen longer. The cosmic dawn unfolded irregularly across space, and because radiation affects gas behavior strongly, this process influenced future galaxy formation too. Heating surrounding gas can suppress additional star formation in some regions by preventing collapse. Meanwhile, supernova explosions blasted enriched material into intergalactic space, altering chemistry everywhere they reached. The young universe was full of feedback loops. Stars altered galaxies. Galaxies altered surrounding gas. Gas influenced future star formation. Everything interacted dynamically, and all of it happened astonishingly early. Now, supernovae deserve special attention because the earliest generations of stars likely exploded frequently. Massive stars live short lives. A giant primordial star may burn through its nuclear fuel in only a few million years before collapsing catastrophically, and when such stars die, the resulting explosions release staggering amounts of energy. For a brief period, a supernova can outshine entire galaxies. The explosion generates shock waves racing through surrounding gas clouds, compressing some regions while dispersing others. Heavy elements forged inside stellar cores spread outward across space. Carbon, oxygen, silicon, iron, the raw materials for future planets and life itself. Without supernovae, the universe would remain chemically primitive. No rocky worlds, no oceans, no biology. No nervous systems mysteriously deciding that midnight is the perfect time to remember embarrassing conversations from 6 years ago. Supernovae transformed cosmic chemistry permanently, and in the young universe they likely occurred everywhere. One generation of giant stars formed quickly, exploded quickly, enriched surrounding gas. Then new generations of stars emerged from increasingly complex environments. The cosmos evolved chemically with remarkable speed. Now, another major source of chaos in the early universe involved black holes, and this remains one of the most puzzling areas in modern astrophysics. Webb has discovered evidence suggesting surprisingly massive black holes already existed in some very early galaxies. That creates a problem, because growing supermassive black holes requires time, or at least scientists thought it did. Black holes increase mass by accreting matter. Gas falls inward, forming hot accretion disks that radiate enormous amounts of energy. Under certain conditions, active black holes become quasars, some of the brightest objects in the universe. But building giant black holes rapidly after the Big Bang is difficult according to many traditional growth models. So how did they appear so early? Astronomers are actively debating possibilities. Maybe primordial giant stars collapsed into unusually massive seed black holes. Maybe accretion rates in the early universe were far more aggressive. Maybe dense environments allowed runaway growth, or perhaps black holes formed through mechanisms not yet fully understood. Again, the young universe keeps behaving more productively than expected, and black holes themselves strongly influence surrounding galaxies. Active black holes generate intense radiation and powerful outflows capable of heating or ejecting gas. This feedback alters future star formation and galactic evolution. So the early cosmos contained galaxies colliding constantly while stars exploded, radiation spread, black holes fed aggressively, and gas moved turbulently through dense environments. Hardly peaceful. Now, despite this violence, or perhaps because of it, the universe became creative remarkably quickly. That's one of the paradoxes of cosmic evolution. Chaos generates structure. Collisions trigger star formation. Supernovae create chemical complexity. Black holes regulate galaxy growth. Violence drives creation. And perhaps nowhere is that more evident than in the galaxies Webb now observes from near the cosmic dawn. JADES-GS-Z 14-0 likely existed inside an environment of extraordinary turbulence. Nearby galaxies may have interacted gravitationally. Intense radiation flooded surrounding space. Massive stars lived and died rapidly. Gas clouds collapsed continuously into new stellar populations. The galaxy we observe as a faint reddish smudge probably represented a wildly energetic place. And that's important because modern images of galaxies often feel calm. Spiral galaxies drifting elegantly through darkness, nebulae glowing softly, everything appearing still and serene. But cosmic history is dynamic. Galaxies evolve through constant interaction and transformation. The early universe especially resembled a gigantic evolving ecosystem, where gravity, radiation, matter and energy continuously reshaped one another. Nothing remained static. Now, another reason the young universe felt so chaotic involves simple scale. The cosmos contained enormous amounts of gas available for star formation. Today, many mature galaxies have already consumed substantial fractions of their star-forming material. Star formation in the modern universe proceeds more slowly overall than during its earlier epochs. But during the cosmic dawn, fresh gas remained abundant almost everywhere. Galaxies could grow rapidly, because fuel existed in enormous quantities. And when galaxies collided, gas compressed into dense regions, triggering intense bursts of stellar birth. Some early galaxies may have formed stars at rates hundreds of times greater than the Milky Way produces today. Imagine entire galaxies behaving like giant cosmic furnaces, converting gas into stars at astonishing speed. That appears to have been relatively common during the young universe. Again, Webb keeps revealing a cosmos far more active than many expected. Now, one emotionally fascinating aspect of all this is how quickly order emerged from apparent chaos. The early universe was turbulent, violent, dense. And yet from that turbulence came galaxies, stars, heavy elements, eventually planets and biology. The chaos was not random destruction without consequence. It was productive instability. And perhaps that mirrors something fundamental about nature itself. Stable, beautiful structures often emerge from dynamic processes rather than perfect stillness. Galaxies form through collisions and gravity. Stars form through collapse and pressure. Planets form through turbulent disks of gas and dust. Even life on Earth evolved through competition, mutation, extinction, and environmental upheaval. Creation rarely arrives through calm simplicity alone. The cosmos builds through transformation. Now, astronomers studying Webb observations are trying to reconstruct this violent era in increasing detail. Spectroscopy reveals chemical composition. Brightness estimates reveal star formation rates. Galaxy shapes hint at mergers and interactions. Researchers are effectively becoming cosmic archaeologists, reconstructing ancient environments from faint infrared signals crossing billions of years of space and time. And the deeper they look, the more dynamic the young universe appears, which makes sense in hindsight. The early cosmos contained enormous energy densities, abundant gas, frequent interactions, and rapidly evolving structures. Of course it was chaotic. The universe was young. Young things tend to be energetic. Just ask any parent who has consumed coffee. while watching toddlers discover gravity experimentally using household objects. Now, one especially profound realization emerging from all this is that the calm modern universe we inhabit is actually the product of billions of years of evolution. The cosmos gradually settled, galaxy collision rates decreased, star formations slowed overall, matter spread farther apart through expansion. The universe aged. But the ancient galaxies Webb observes belong to a much more turbulent epoch, and somehow, despite all that violence, light from those galaxies survived. Photons escaped intense stellar environments, crossed expanding space for over 13 billion years, and finally reached Webb's mirrors near L2. Ancient radiation carrying information from one of the most chaotic periods in cosmic history. There's something wonderfully strange about that. The universe preserves its own history through light. Even violent ancient events leave traces detectable billions of years later. And now humanity has finally built instruments sensitive enough to read those traces directly. Still, Webb has likely revealed only the beginning. More observations will come, more early galaxies, more evidence of violent star formation and rapid evolution. Possibly even earlier structures still hidden near the edge of detectability. The cosmic dawn remains partly mysterious. But one thing already seems clear. The early universe was not a quiet waiting room before real cosmic history began. It was one of the most active and transformative eras the cosmos has ever known. One of the quietest but most important realizations in astronomy is that the universe changes its behavior over time, not just superficially, fundamentally. The cosmos you see tonight is not the cosmos that existed 13 billion years ago. Galaxies were different, stars were different, chemistry was different, even intergalactic space itself behaved differently, and galaxies like JADES-GS-Z 14-0 matter because they allow humanity to study those changes directly, instead of merely imagining them through theory. In a sense, Webb has transformed the early universe from a mathematical idea into an observable place, a very strange place, a very active place, and perhaps a place evolving far faster than scientists once believed. Now, before Webb, astronomers already understood broad outlines of cosmic evolution reasonably well. The Big Bang produced a hot expanding universe dominated initially by hydrogen and helium. Tiny fluctuations in density gradually grew under gravity. The first stars ignited, galaxies formed, heavy elements accumulated through stellar evolution. Eventually planets emerged. That overall story remains strongly supported. But broad outlines are not the same thing as detailed understanding, and JADES-GS-Z 14-0 is revealing something important about the details. Namely, the universe appears remarkably efficient at building complexity, earlier than expected. Now, complexity in cosmology does not necessarily mean life or intelligence or philosophical discussions at 2 a.m. about whether soup technically counts as a beverage. It means structure, galaxies, stars, chemical enrichment, large organised systems emerging from relatively simple beginnings, and according to many earlier models, those processes should require substantial time. Yet Webb keeps finding evidence suggesting the young universe became structurally rich astonishingly quickly. JADES-GS SID 14-0 existed only around 290 million years after the Big Bang. That is barely the opening stretch of cosmic history, and yet the galaxy already appears luminous enough to imply active star formation and substantial organisation, which tells astronomers something profound. The universe does not hesitate long once conditions permit structure to emerge. Gravity begins building immediately. Now, one of the most important insights from galaxies like JADES-GS-Z 14-0 concerns the pace of early star formation. The first stars transformed the cosmos by producing radiation and heavier elements. Without stars, the universe would remain chemically primitive forever. But Webb suggests star formation may have accelerated rapidly during the earliest epochs. The cosmic dawn appears less like a gradual sunrise and more like an enormous chain reaction spreading across the young universe. Stars ignited, galaxies assembled, radiation ionized surrounding hydrogen, chemistry evolved. Everything began happening very quickly, and that reshapes our understanding of how the universe matured. For decades, many astronomers imagined early galaxies as tiny, fragile systems, slowly growing through incremental mergers and gradual star formation. Some certainly were, but Webb reveals that substantial luminous galaxies already existed astonishingly early. That means cosmic evolution may proceed more aggressively than previously assumed under the right conditions. The young universe was productive, very productive. Now, another major implication involves Reionization. This period remains one of the most important transitions in cosmic history. After recombination, the universe contained mostly neutral hydrogen gas. During the cosmic dark ages, space remained relatively opaque to ultraviolet radiation, because neutral hydrogen absorbs it efficiently. Then the first stars and galaxies change everything. Their radiation ionized surrounding gas, gradually transforming intergalactic space. The universe became transparent again over large scales. But exactly how and when this occurred remains one of cosmology's great questions. Galaxies like JADES-GS-Z 14-0 provide valuable clues because they existed directly during this transformative era. If bright galaxies already populated the universe by Redshift 14, they may have contributed substantially to Reionization itself. In other words, galaxies were not merely passive objects forming inside the cosmos. They were actively reshaping the universe around them, tiny regions of star formation, influencing the state of intergalactic space across enormous distances. And perhaps that reveals something deeper about cosmic evolution generally. Nothing evolves independently. Galaxies influence surrounding gas. Radiation affects future star formation. Supernova alter chemistry. Black holes regulate galactic growth. The universe evolves through interconnected feedback processes constantly interacting across vast scales. Everything affects everything else. Now, JADES-GS-Z 14-0 also reveals something fascinating about timing. Human intuition tends to underestimate how quickly nature can organize matter under the influence of gravity. Given billions of years, anyone expects galaxies eventually. But Webb suggests galaxies emerged very early indeed. The first large structures may have assembled astonishingly soon after the Big Bang. And perhaps this should not surprise us completely. Gravity is cumulative. Tiny density fluctuations grow larger over time. Regions containing slightly more matter attract additional matter, strengthening the process continuously. Once collapse begins, structure formation can accelerate rapidly, especially in a denser young universe where galaxies existed closer together and interactions occurred frequently. The cosmos may naturally favour rapid organisation under early conditions, and that realisation changes how astronomers think about the transition from simplicity to complexity. The universe may not require long dormant ages before creativity begins. Complexity appears remarkably quickly once physical conditions allow it. Now, another implication concerns chemical evolution. The earliest universe contained mostly hydrogen and helium. Heavy elements formed later through stellar fusion and supernova explosions. This means galaxies like JADES-GS-Z 14-0 existed during one of the first major phases of chemical enrichment in cosmic history. Inside those early stars, the universe began manufacturing the ingredients required for future planets and biology. Carbon, oxygen, silicon, iron, the building blocks of rocky worlds and living systems. Webb observations help astronomers investigate how quickly this chemical evolution began, And the answer again appears to be surprisingly fast. The young universe may have become chemically complex earlier than expected. One generation of stars formed and died rapidly. Heavy elements spread into surrounding gas. Future generations of stars inherited enriched environments. The cosmos evolved chemically through feedback loops operating across astonishingly short cosmological timescales, and eventually, billions of years later, those processes produced planets like Earth, which means galaxies like JADES-GS-Z 14-0 belong not only to ancient cosmic history, they belong to the beginning of our own material story. The oxygen in your lungs originated through stellar evolution. The calcium in your bones formed inside stars. The iron in your blood emerged through ancient nuclear processes. Human beings are products of cosmic chemical evolution, and early galaxies represent the opening chapters of that process. Now, there's also an important lesson here about observation itself. Before Webb, humanity could theorize about the cosmic dawn but lacked detailed direct evidence. The earliest galaxies remained partly hidden behind technological limits. Then suddenly a new telescope opened deeper infrared windows into the young universe, and the cosmos revealed something unexpected. This pattern appears repeatedly throughout scientific history. New instruments change reality. Not reality itself, of course, but humanity's accessible version of reality. Galileo pointed telescopes toward Jupiter and discovered moons orbiting another world. Hubble revealed expanding galaxies, radio astronomy uncovered invisible cosmic structures, and Webb is now exposing the universe's earliest galaxies with astonishing detail. Technology changes perspective. Perspective changes theory. Theory changes understanding. The process never really ends. Now, one subtle but profound implication of Webb's discoveries involves the universality of physical law. Think about what JADES-GS-Z 14-0 actually demonstrates. Light emitted over 13.5 billion years ago behaves according to the same physical principles we observe today. Gravity worked. Nuclear fusion worked. Electromagnetism worked. Atomic physics worked. The same laws governing stars and galaxies now also governed them near the dawn of cosmic history. That consistency, across billions of years and unimaginable distances, remains one of the most astonishing facts in science. The universe is comprehensible because physical law appears stable. Without that stability, astronomy itself would collapse into chaos. Instead, photons from ancient galaxies carry understandable information across cosmic time, and humanity can decode it. Now, there's another fascinating consequence of all this. Galaxies like JADES-GS-Z 14-0 suggest that mature-looking structure may emerge naturally and repeatedly throughout the universe under suitable conditions. The cosmos seems remarkably good at building galaxies, not eventually after endless waiting, quickly, perhaps inevitably. Given matter, gravity, and time, the universe appears strongly biased toward producing organized structure, and perhaps that has broader implications we do not yet fully understand. After all, galaxies themselves create environments where stars form. Stars produce heavy elements. Planets emerge. Complex chemistry becomes possible. Maybe cosmic evolution naturally trends toward increasing structural richness over time. Not through intention, not through destiny, simply through the behavior of physical law. Gravity gathers matter, stars forge elements, evolution builds complexity step by step. The process unfolds automatically, and Webb is now allowing humanity to witness its earlier stages directly. Now, astronomers remain cautious, of course. That is important. One galaxy alone cannot overturn cosmology. Researchers continue gathering data, refining models, improving simulations, and testing interpretations. Science progresses carefully, but already galaxies like JADES-GS-Z 14-0 are influencing how researchers think about early cosmic evolution. The young universe appears more active than expected, more crowded, more chemically productive, more efficient at assembling galaxies, and future discoveries may deepen these conclusions further. Webb continues observing ancient galaxies constantly. Additional high redshift systems continue emerging from surveys. Some may prove older, some may reveal surprising chemical signatures, some may contain unexpectedly massive black holes. The early universe still holds enormous mysteries. Now, emotionally speaking, one of the most striking things about JADES-GS-Z14-0 is how it alters humanity's sense of cosmic timing. Before Webb, the earliest universe often felt abstract and inaccessible, a dark, primitive era preceding real galactic history. Instead, Webb reveals a cosmos already alive with structure astonishingly early. The darkness after the Big Bang did not last forever. The first stars switched on quickly. Galaxies emerged rapidly. Radiation spread. Chemistry evolved. The universe became dynamic almost immediately. And somehow, after billions of years of evolution, one species developed the ability to observe that process happening. There's something deeply calming about that continuity. The same universe that produced early galaxies eventually produced observers capable of understanding them. Ancient photons travelled patiently across cosmic history, while stars formed, exploded, and enriched space with heavier elements. Galaxies merged, planets formed, life emerged, civilizations developed, and finally telescopes near L2 began collecting light from the cosmic dawn. Everything connected through one continuous unfolding history. Now, there's still much Webb cannot yet tell us. We do not fully understand how the first stars formed. We do not know precisely how rapidly the earliest black holes grew. We still struggle to explain all the unexpectedly bright galaxies Webb observes. And somewhere beyond current detection limits, even older galaxies likely wait hidden in the darkness. But JADES-GS-Z14-0 already reveals something profound. The universe became recognizable very early. Not complete, not calm, not mature, but recognizable. Gravity was already building galaxies, stars were already forging elements, radiation was already reshaping intergalactic space. The cosmic story we inhabit had already begun astonishingly soon after the beginning itself. One of the most dangerous phrases in astronomy is the oldest known. Scientists use it carefully because history suggests those words rarely survive for long. The universe has a habit of hiding something older just beyond the edge of current technology. For centuries, humans thought the Milky Way was the entire cosmos. Then telescopes improved and revealed other galaxies. Astronomers once debated whether galaxies even existed outside our own. Then Edwin Hubble measured their distances and the universe suddenly became vastly larger overnight. Later, researchers believed certain quasars represented the farthest observable objects. Then more sensitive instruments discovered galaxies farther away still. And now, JADES-GS-Z14-0 stands among the oldest galaxies humanity has ever observed. But almost nobody expects it to keep that title forever, because Webb has only just begun looking, and the universe almost certainly contains even older galaxies still waiting in the darkness. Now, this possibility is not simply optimism or scientific ambition speaking. It follows naturally from cosmology itself. The first stars and galaxies did not appear all at once simultaneously across the entire universe, like synchronized decorative lights switching on during a holiday display. Structure formation happened gradually and unevenly. Some regions likely formed stars earlier than others, depending on local density fluctuations and dark matter distribution. Certain areas may have produced primitive galaxies astonishingly quickly. Others remained dark longer. The cosmic dawn unfolded across space in patchwork fashion. Which means somewhere out there, ancient galaxies older than JADES-GS-Z 14-0 almost certainly existed. The real question is whether humanity can see them, and that question depends on light. Everything depends on light. Astronomy is fundamentally limited by photons reaching us across cosmic time. If ancient galaxies emitted enough radiation, and if that radiation survived the journey across expanding space long enough to arrive at our telescopes, then perhaps Webb can detect them. But eventually cosmology itself imposes boundaries. Now, one important thing to understand is that observing older galaxies becomes dramatically harder very quickly. Not gradually harder, exponentially harder. Because the farther back astronomers look, the younger and smaller galaxies become. Their stars are fewer, their luminosity decreases, their light stretches more severely into infrared wavelengths through cosmic expansion. And surrounding neutral hydrogen gas in the early universe absorbs ultraviolet radiation strongly, complicating observations further. The cosmic dawn is difficult to observe partly because the universe itself was not yet fully transparent. Imagine trying to study fireflies through fog while the fireflies themselves remain tiny and distant and the fog continuously thickens. That begins approaching the challenge astronomers face when searching for the earliest galaxies, and yet Webb keeps succeeding astonishingly well, which is why researchers remain hopeful. Now, another reason scientists expect older galaxies to exist involves statistics. The observable universe contains hundreds of billions, perhaps trillions of galaxies overall. Even during very early cosmic epochs, enormous numbers of structures likely formed across vast regions of space. Webb surveys only tiny fractions of the sky at extreme depth. Tiny fractions. That's one of the strangest things about deep field astronomy. When telescopes stare into apparently empty darkness for long exposures, they reveal staggering numbers of galaxies hidden inside minuscule regions of sky. A small patch of darkness can contain thousands of galaxies, entire cosmic histories packed into what initially looks empty. So if JADES-GS-Z 14-0 emerge from the areas Webb has already examined, statistically there may be additional ancient galaxies scattered elsewhere across the observable universe. Possibly older ones, possibly stranger ones, possibly systems challenging cosmology even further, and perhaps some ancient galaxies remain just barely below current detection thresholds. Their photons already arrive at Webb's mirrors, but not yet in sufficient quantity for confident identification. That idea feels wonderfully haunting somehow. Ancient light crossing billions of years of space, reaching humanity quietly, while still remaining almost invisible. Messages from the cosmic dawn hovering at the edge of detectability. Now, astronomers searching for earlier galaxies often rely on increasingly deep, infrared observations combined with spectroscopy. Infrared matters because cosmic expansion stretches ancient light enormously. A galaxy emitting ultraviolet radiation near the dawn of time may appear today only in deep infrared wavelengths, which is exactly why the James Webb Space Telescope was designed the way it was. Webb exists specifically to peer deeper into cosmic history than previous observatories could manage, and even now researchers continue refining observational techniques, longer exposures, improved calibration, more sophisticated data analysis, advanced simulations helping identify candidate high redshift galaxies. Astronomy evolves alongside technology constantly. Each improvement extends the observable horizon slightly farther. Now, one fascinating possibility involves galaxies forming even earlier than many current models comfortably allow. If JADES-GS-Z 14-0 already appeared surprisingly mature at redshift 14, perhaps the first generations of galaxies assembled extraordinarily rapidly. Maybe the universe transitioned from darkness to structure faster than scientists imagined. Again, Webb keeps hinting at a young cosmos more productive than expected, and if that trend continues, astronomers may eventually discover galaxies existing only 200 million years after the Big Bang. Maybe earlier. That would push observations astonishingly close to the first stars themselves. Now, eventually there must be a limit. Galaxies cannot form instantly after the Big Bang. The universe required time for expansion, cooling, dark matter halo formation, gas collapse, and star formation. Physics imposes constraints. The first stars likely needed at least tens of millions of years to appear. Galaxies required additional time beyond that. So astronomers do not expect fully formed galaxies immediately after cosmic inflation or during the first moments of the universe. Still, the timeline may be shorter than previously assumed, and that possibility excites cosmologists enormously, because every earlier galaxy discovered provides new information about how quickly structure emerged from primordial simplicity. Now, there's another deeply interesting aspect to this search. Eventually, astronomers may reach objects so distant that they no longer resemble galaxies in the modern sense at all. Instead, researchers might observe tiny, primitive stellar systems, proto-galaxies, or clusters dominated by the first generations of stars. The boundary between first stars and first galaxies may blur considerably. After all, galaxies evolved gradually. The universe did not suddenly invent fully mature spiral galaxies overnight. Early systems were chaotic collections of gas, dark matter, radiation, and rapidly forming stars. Messy cosmic construction zones. And somewhere among those primitive structures lies the true beginning of galactic history itself. Astronomers are trying to find it. Now, another possibility researchers discuss involves gravitational lensing. Gravity bends light. Massive objects like galaxy clusters distort space-time strongly enough to magnify more distant galaxies behind them. Nature creates its own telescopes. This effect allows astronomers to observe objects that would otherwise remain too faint. Webb already uses gravitational lensing in some observations to peer deeper into the early universe, and perhaps future surveys using lensing strategically will uncover galaxies even older than JADES-GS-Z 14-0. Tiny ancient systems amplified by cosmic geometry itself. The universe helping humanity observe its own beginnings. There's something strangely elegant about that. Now, despite all this excitement, astronomers remain cautious for good reason. Extreme redshift measurements are difficult. Very distant galaxies appear faint and tiny. Interpreting observational data requires careful spectroscopy and modelling. Some candidate ancient galaxies eventually turn out to be closer dusty galaxies, masquerading as more distant objects. The universe enjoys practical jokes occasionally, so researchers verify these discoveries carefully. Redshift measurements, spectral analysis, brightness estimates, multiple independent observations. The process is meticulous because extraordinary claims require strong evidence. Still, Webb's track record so far has already exceeded many expectations. The telescope keeps revealing ancient galaxies from astonishingly early cosmic epochs. And importantly, Webb is not operating near failure or exhaustion. This is still relatively early in the mission. More surveys will come, deeper observations will happen, additional ancient galaxies almost certainly await discovery. Now, there's also a more philosophical side to this search. Every older galaxy humanity discovers moves the observable frontier closer to the beginning itself. Closer to the first stars, closer to the end of the cosmic dark ages, closer to the transition from a relatively simple universe into one filled with structure and light. Astronomy is gradually approaching the earliest visible chapters of cosmic history. And perhaps one day future telescopes will observe evidence from epochs even Webb struggles to reach. There are already concepts for next-generation observatories designed to push farther into the infrared and deeper into cosmic time. Human curiosity rarely stops at the current horizon. Once people glimpse ancient galaxies, naturally they want older ones, then older still. Eventually humanity may attempt to observe the very first luminous objects ever formed. And beyond that lies another profound limit: the cosmic microwave background itself. Earlier than recombination, the universe remained opaque to ordinary light. Photons scattered continuously through hot plasma. No traditional telescope can directly see beyond that wall because visible radiation could not travel freely yet. In a sense, the early universe hides its deepest infancy behind a veil. Still, astronomers are extraordinarily creative. Researchers study gravitational waves, neutrinos, and subtle signatures inside the cosmic microwave background itself, searching for clues about even earlier epochs. Humanity continues finding new ways to ask ancient questions. Now, emotionally speaking, there is something wonderfully comforting about the idea that older galaxies probably still wait undiscovered in the darkness. The universe remains unfinished from our perspective. Mystery survives. Human knowledge expands continuously but never completely. And every time telescopes reveal something astonishing, reality quietly hints at additional hidden layers beyond current understanding. JADES-GS-Z 14-0 feels ancient because it stretches human observation deep into cosmic history. Yet it may eventually become only one milestone among many, a stepping stone toward even earlier discoveries. One day, future astronomers may casually discuss galaxies older still, while treating JADES-GS-Z 14-0 as an important but intermediate discovery. Science often works that way. Each frontier eventually becomes history. Now, somewhere in the observable universe tonight, photons from even older galaxies may already be travelling toward us. Some began their journey before JADES-GS-Z 14-0 emitted the light Webb detected. They have crossed expanding space for over 13 billion years already, passing galaxies, crossing dark intergalactic voids, surviving cosmic evolution itself, and perhaps eventually some of those photons will strike the mirrors of Webb or future telescopes. Humanity simply has not noticed them yet. There's something deeply peaceful about that thought. The universe still contains ancient stories waiting patiently to be read. Light from the earliest epochs continues arriving slowly across cosmic time, and somewhere beyond the current horizon of knowledge, older galaxies almost certainly remain hidden inside the darkness before dawn fully arrived. Perhaps the strangest thing about astronomy is that it turns distance into memory. That sounds poetic at first, almost like the sort of sentence someone would write beneath a blurry photograph of the moon on social media, before disappearing mysteriously into a career selling scented candles. But in cosmology, it is literally true. The farther away something exists, the older the light becomes by the time it reaches us. Distance and time become inseparable, and galaxies like JADES-GS-Z 14-0 force the human mind into a very unusual realization. When we observe the distant universe, we are not seeing what exists now, we are seeing what once existed. Astronomy is not observation in the ordinary sense, it is delayed experience. Now, human beings evolve to navigate immediate environments, nearby sounds, nearby faces, nearby threats. Our instincts assume sight reveals the present moment. If you look across a room, your brain naturally assumes you're seeing reality as it exists right now. And technically you are more or less, because light crosses ordinary human distances extremely quickly. But even in everyday life, you never truly see the present. You see slightly delayed light. The delay is simply too tiny for your brain to notice. Light from another person's face takes a fraction of a second to reach your eyes. Sunlight arriving this afternoon left the sun about 8 minutes earlier. If the sun somehow vanished instantly, Earth would continue orbiting peacefully for those 8 minutes before anything changed visibly. Which is a mildly unsettling thought, best not examined too intensely before trying to sleep. Still, once you move into astronomy, these delays become enormous. The moon appears as it existed about 1.3 seconds ago. Jupiter appears dozens of minutes in the past. Nearby stars appear years in the past. Distant galaxies appear millions or billions of years ago. And JADES-GS-Z 14-0, that galaxy appears from over 13.5 billion years ago. The light Webb detected began its journey before Earth existed, before the Sun formed, before the Milky Way looked remotely familiar, and only now has that ancient radiation finally arrived. There is something deeply strange about that. Right now, somewhere in the universe, JADES-GS-Z 14-0 almost certainly no longer resembles the object Webb observed. If it still exists at all in recognizable form, it has evolved enormously across cosmic time. Stars have formed and died. Perhaps galaxy mergers reshaped it completely. Black holes may have grown. Chemical composition changed. The galaxy continued evolving for billions of years after the light we observed departed. But humanity cannot see any of that yet. The newer light has not arrived, which means every telescope functions as a machine for observing different layers of history simultaneously. The night sky is not a collection of objects existing in one shared moment. It is a mosaic of times. Some stars appear relatively recent, others appear ancient. Every visible object belongs to a different era, and once you fully absorb that idea, the universe begins feeling profoundly unfamiliar in a fascinating way. Even the stars overhead stop seeming immediate. Now, one especially important consequence of this involves the observable universe itself. People sometimes imagine the universe as a giant space humans could theoretically travel across given enough time and sufficiently irresponsible engineering decisions. But cosmology imposes deeper limits. Because the universe has a finite age, there exists a maximum distance from which light could have reached us since the Big Bang. This defines the observable universe, not the entire universe necessarily, just the portion whose light has had enough time to arrive. Beyond that horizon, more cosmos almost certainly exists, possibly endlessly, but its light remains unreachable for now. The observable universe is essentially a sphere of accessible history centered around Earth, and that sphere changes constantly as time passes and more distant photons arrive. Humanity lives inside an expanding archive of cosmic memory. Now, this becomes even stranger because cosmic expansion continuously stretches space-time itself. The universe is not static while light travels through it. Distances between galaxies increase over time, which means when astronomers say JADES-GS-Z 14-0 lies over 13.5 billion light-years away, that statement becomes complicated. The galaxy was much closer when the light began its journey. Over billions of years, expanding space increased the separation enormously. Today, the galaxy's actual present-day distance is vastly larger, possibly over 30 billion light-years away, which sounds impossible initially because people naturally assume nothing should exceed the age of the universe multiplied by the speed of light. But cosmic expansion changes the geometry itself. Galaxies are not necessarily racing through space faster than light in the ordinary sense. Space itself expands. Again, this is usually the point where the human brain begins politely requesting soup and a nap. Still, the core reality remains extraordinary. Light from JADES-GS-Z 14-0 travelled across a universe changing continuously during its journey. Galaxies formed, stars exploded, expansion stretched wavelengths, entire cosmic eras passed, and the photons simply continued moving patiently through space-time until finally striking Webb's mirrors near L2. Now, another strange aspect of observing the past involves causality. When astronomers study ancient galaxies, they are observing events that no longer exist. The stars producing that light may have died billions of years ago. Some galaxies observed today may have merged into larger systems long before Earth formed. Astronomy constantly reveals vanished states of reality. In a sense, telescopes see ghosts. Not supernatural ghosts, obviously. Physical ghosts. Ancient light preserving moments long gone. And perhaps nowhere does that feel more emotionally powerful than when observing galaxies near the cosmic dawn. JADES-GS-Z14-0 belongs to an era unimaginably distant from ordinary human experience. When its light began travelling, the observable universe itself was radically different. The cosmos remained denser, younger, more chaotic. Intergalactic hydrogen still existed partly in neutral form. The first generations of stars and galaxies were actively reshaping space through radiation and chemical enrichment, and somehow humanity can observe that epoch directly. That remains astonishing. Now, one reason this matters scientifically is because observing ancient light allows astronomers to reconstruct cosmic evolution. The farther away a galaxy exists, the younger the universe appears around it. By observing galaxies from many different distances, researchers effectively assemble a time-lapse record of cosmic history. Nearby galaxies reveal later stages of evolution. Distant galaxies reveal earlier stages, and galaxies like JADES-GS-Z14-0 show the universe astonishingly close to its beginning. Astronomy becomes a historical science conducted through direct observation. That is extraordinarily rare. Most sciences reconstruct the past indirectly through evidence preserved in the present. Astronomers literally observe earlier epochs because light itself carries delayed information across time. The cosmos records its own history automatically. Now, there's also something philosophically unsettling about this arrangement. The present moment of the universe remains fundamentally inaccessible beyond your immediate surroundings. You cannot observe Andromeda now. You see it as it existed 2.5 million years ago. You cannot observe distant galaxies now. You see ancient states frozen in light. Even the nearest star beyond the Sun appears years outdated. The observable universe is always historical. Reality itself outruns observation continuously. And perhaps that reveals something profound about existence. The universe is not given to us instantaneously. Knowledge always arrives delayed. Now, despite this delay, physical law remains astonishingly consistent across cosmic history. That's one of the great triumphs of astronomy. The same atomic physics governing light today also governed light over 13 billion years ago. Spectral lines behave predictably. Gravity behaves predictably. Fusion behaves predictably. Because physical law remains stable, ancient photons remain interpretable. Human beings can decode messages emitted before Earth existed. That consistency across unimaginable distances and timescales is one of the most remarkable facts in science. Now, there's another emotional consequence of all this that people sometimes overlook. The night sky becomes less lonely once you realize you are surrounded by history constantly arriving. Ancient light fills space continuously. Photons from distant galaxies pass through Earth every second, carrying information from eras humanity never experienced directly. Some photons striking your body tonight may have travelled billions of years uninterrupted. The universe constantly touches the present with pieces of its past. And Webb exists because humanity learned how to read those messages carefully. The telescope captures faint infrared radiation from galaxies near the dawn of time and transforms it into data, images, and spectra humans can understand. That process feels almost miraculous even though it rests entirely on physics and engineering. A giant infrared telescope drifting through space allows one species on one planet to observe light, emitted billions of years before their world formed. Civilization occasionally achieves breathtaking things. Now, JADES-GS-Z14-0 also changes humanity's emotional relationship with time itself. Human history feels enormous to individuals. Ancient civilizations seem unimaginably distant. Thousands of years stretch beyond ordinary comprehension. But cosmology expands temporal perspectives so dramatically that human history becomes almost invisible by comparison. The entire span of recorded civilization occupies a tiny fraction of cosmic time. Dinosaurs vanished relatively recently on astronomical scales. Even Earth itself formed surprisingly late compared to the age of the universe. And yet despite arriving so late, humanity developed the ability to observe ancient galaxies from near the beginning. There is something strangely beautiful about that timing. The universe spent billions of years evolving stars, galaxies, and heavy elements before observers appeared capable of understanding cosmic history. And now here we are, briefly awake inside that history. Now, another curious thing about looking into the past is that it also means looking toward origins. The farther astronomers peer into space, the closer they approach the first stars, the first galaxies, the end of the cosmic dark ages itself. Every increase in observational power pushes humanity nearer the beginning of visible cosmic structure. Webb already revealed galaxies existing astonishingly early. Future telescopes may go farther. Perhaps eventually humanity will observe the very first luminous objects ever formed, and beyond that lies the ultimate wall. Before recombination, the universe remained opaque to ordinary light. Photons scattered continuously through hot plasma. No traditional telescope can directly observe earlier epochs through electromagnetic radiation, because the cosmos itself was opaque. There exists a visible limit to cosmic history, at least for now. Still, astronomers continue searching for indirect ways to probe even earlier eras through gravitational waves, neutrinos, and subtle patterns inside the cosmic microwave background. Human curiosity keeps pushing toward deeper origins relentlessly. Now, emotionally speaking, perhaps the most calming part of all this is realizing that the universe does not disappear into the past completely. Its history remains physically present through light. Ancient galaxies still communicate across time simply by existing long enough for their photons to arrive. The cosmos preserves memory automatically, and every night above Earth, ancient light continues crossing the sky silently. Some photons visible tonight began travelling before humanity existed. Others departed before Earth formed. And somewhere in the darkness beyond current observation, even older light still moves patiently toward future telescopes and future generations. The universe is full of delayed stories still arriving, and so tonight, after travelling backward across billions of years, we arrive at something strangely quiet. Not an explosion, not a final revelation hidden dramatically at the centre of the cosmos, just light, very old light, light that spent almost the entire lifetime of the universe crossing space patiently before finally reaching us. When the photons from JADES-GS-Z14-0 first began their journey, nothing familiar to human beings existed yet. No Earth, no moon, no oceans, no mountains, no trees moving in the wind, no animals sleeping beneath dark skies. Not even the Milky Way had fully become the galaxy we know today. The universe itself was still young, chaotic, crowded, filled with violent star formation, radiation, collisions, and giant stars living brief, brilliant lives inside primitive galaxies. And somewhere during that astonishingly early era, a galaxy emitted light into expanding space. The photons travelled onward, year after year, million after million years. The universe expanded around them continuously. Galaxies merged, stars exploded, black holes formed, heavy elements spread through interstellar space, entire cosmic epochs passed. Still, the light continued. When those photons began their journey, Earth was still billions of years away from existing. Then eventually our planet formed around a young star near the edge of an ordinary galaxy. Oceans appeared, life emerged, cells evolved, dinosaurs ruled and vanished. Mammals spread across continents, humans appeared astonishingly recently. Civilizations rose. People learned mathematics and optics and engineering. They built telescopes, then observatories, then rockets, then giant infrared mirrors drifting through space beyond the moon. And finally, after more than 13.5 billion years of travel, ancient photons from JADES-GS-Z 14-0 reached the James Webb Space Telescope. There is something deeply emotional about that chain of events. Not sentimental exactly, more humbling. The universe spent billions of years evolving toward a moment where one species could finally notice ancient light arriving from near the beginning of cosmic history. And perhaps that is one of the strangest things astronomy reveals. The cosmos is not static scenery surrounding human existence. We are part of the same unfolding process. The earlier stars forged heavier elements. Those elements became planets. Those planets allowed chemistry to become increasingly complex. Eventually somewhere, at least once that we know of, matter learned how to become conscious enough to ask questions about itself. And now humans lie awake at night wondering about galaxies older than almost everything. There's a beautiful continuity in that. Now JADES-GS-Z 14-0 itself may no longer resemble the galaxy Webb observed. The light we see belongs to an ancient moment frozen in transit. Meanwhile, the galaxy continued evolving for billions of years beyond that snapshot. Perhaps it merged into larger structures. Perhaps stars formed and died there for ages afterward. Perhaps giant black holes grew inside it. Or perhaps the galaxy itself no longer exists in recognizable form at all. We do not know. The newer light simply has not reached us yet. That idea still feels wonderfully strange. Astronomy allows humanity to observe vanished realities. The night sky becomes a history book written in photons. Every distant object represents another time, another era, another chapter in cosmic evolution still arriving across space. And the farther outward we look, the farther backward the universe reveals itself. Now, one of the most comforting things about cosmology is how thoroughly it reshapes human perspective. Ordinary life often feels urgent. Schedules, deadlines, notifications, tiny glowing clocks insisting it is somehow already later than expected. But the universe operates on scales so enormous that urgency begins dissolving. Galaxies evolve across billions of years. Stars live and die over unimaginable timescales. Light itself crosses the cosmos patiently without hurry. Nothing in astronomy moves quickly from a human perspective, and perhaps there is peace in that. The cosmos does not rush. Gravity takes its time, stars take their time, galaxies take their time. Even ancient photons reaching Webb tonight began travelling before our species existed and still arrived exactly when physics allowed them to. Now, Webb itself will not last forever. One day the telescope will fall silent. Its instruments will stop operating. Future observatories will replace it. New technologies will emerge, and future generations may look even deeper into the past than Webb ever could. Perhaps astronomers decades from now will discover galaxies older than JADES-GS-Z 14-0. Perhaps they will observe the first generation of stars directly. Perhaps humanity will eventually witness the true beginning of cosmic structure emerging from the darkness after the Big Bang. The frontier keeps moving. That's one of the wonderful things about science. Every answer creates larger questions waiting beyond it, and the universe always seems willing to provide more mystery. Still, no matter what future discoveries come, JADES-GS-Z 14-0 will remain important because it marked a moment when humanity first realized just how quickly the universe became alive with structure. The galaxy showed us that the cosmic dawn arrived astonishingly early, that galaxies assembled faster than expected, that the young universe was more active, more productive, and more creative than many earlier models predicted. Darkness did not last long. The first stars switched on quickly. galaxies emerged rapidly. Complexity spread through the cosmos almost immediately after conditions allowed it, and perhaps that tells us something profound about the universe itself. Given matter, gravity, and time, structure appears naturally. The cosmos seems remarkably good at building stars and galaxies, and eventually, perhaps inevitably, complexity grows from those beginnings. Now, somewhere beyond Webb's current observations, even older galaxies likely still wait in the darkness. Their photons continue travelling toward us tonight, ancient light crossing expanding space silently. Some of it may already be approaching Earth right now. Humanity simply has not detected it yet. There is something deeply calming about that thought. The universe still contains ancient stories waiting patiently to arrive. Now, before we end tonight's journey, take a moment to remember where you are. One small planet orbiting one ordinary star inside one galaxy among trillions. And yet from this tiny world, consciousness emerged capable of understanding that galaxies existed before Earth itself formed. Capable of building machines that capture ancient infrared photons from near the dawn of time, capable of reconstructing cosmic history from faint stretched light crossing billions of years of space. That remains extraordinary. Human beings are small compared to the universe. Astronomy makes that very clear. But small does not mean insignificant. A tiny species on a tiny world still learned how to read the history of the cosmos itself. And tonight, somewhere above Earth, the James Webb Space Telescope continues drifting quietly near L2. Its gold mirrors remain pointed toward darkness, still collecting ancient light, still listening to the oldest stories the universe can tell. And somewhere far beyond the Milky Way, beyond countless galaxies, beyond distances almost impossible to imagine, ancient photons continue their patient journey across expanding space. Some began travelling before Earth existed, some before the Sun existed, and eventually, perhaps billions of years from now, other civilizations on other worlds may look upward and discover ancient light from galaxies humanity has never even seen. The universe will continue unfolding long after us, stars will continue forming, galaxies will continue colliding, light will continue crossing the darkness, patiently, quietly, endlessly. And for a brief moment in cosmic history, we were here to notice it.